Hello there and welcome to Science for Sleep, where we take large scientific subjects, slow them down, and give them enough room to become clear without asking your brain to hurry. Tonight, we are turning our attention toward comets, those small, cold objects that spend most of their existence far from the warmth of a star, only to become bright and active when their paths carry them inward. Perhaps you are listening late at night, with the room quiet and the day finally finished. Perhaps it is early morning where you are, and you have decided that learning about frozen objects moving through deep space is a reasonable way to begin the day. It is certainly calmer than checking the news. Wherever you happen to be, take a moment to notice the time and the place. What part of the world are you listening from, and can you see the sky from where you are? There may be a window nearby, a thin line of light beneath a curtain, or simply a ceiling that leaves the night entirely to the imagination. Comets have a useful way of reminding us that the sky is not a fixed background. It changes. Objects move through it. Some return on schedules that astronomers can predict with impressive accuracy. Others appear with little warning, brighten for a few weeks or months, and then head back into regions so distant that no person alive will see them again. A few pass through once and never return at all. They arrive from outside our solar system, move around the sun, and continue onward, carrying no luggage, offering no explanation, and showing very little interest in our calendars. When most people picture a comet, they imagine a bright point with a long tail stretching behind it. That is understandable. The tail is the part that attracts attention. It can extend across a large section of the sky, and in especially favourable cases it can become visible without a telescope. The solid body at the centre, however, is usually much smaller than the display around it. A comet can produce an enormous cloud of gas and dust while hiding a nucleus only a few kilometres wide. It is a little like discovering that a large fog bank is being organised by something roughly the size of a small town, although the town in this case is dark, frozen, irregularly shaped, and generally unsuitable for public transport. That simple picture, a frozen nucleus surrounded by a glowing cloud and one or more tails, is a good place to begin. It is not the whole story. Comets differ in where they come from, how long they take to orbit, how closely they approach the sun, how strongly they become active, what materials they release, and whether they are still active at all. Some complete an orbit in a few years, some need decades. Others need thousands or millions of years. Some pass so close to the sun that they break apart. Some remain active at distances where water ice should stay firmly frozen. Some behave like asteroids until they unexpectedly release dust. Others once behaved like comets, but have since lost much of the material that allowed them to produce a visible coma and tail. This is why the phrase comet type can mean several different things. Astronomers may classify a comet by its orbital period, by the shape of its orbit, by its likely place of origin, by its physical behaviour, or by the family of objects with which it shares a similar path. The categories can overlap. A comet may be short period, belong to the Jupiter family, produce frequent outbursts, and eventually become dormant. It does not have to select one label and wear it for the rest of its existence. Space classification is rarely that considerate. Across this long discussion, we will move through the major groups used to describe known comets and comet-like bodies. We will meet the frequent visitors whose orbits are strongly influenced by Jupiter. We will look at Halley-type comets, which return over human timescales but do not come around often enough to become familiar neighbours. We will follow long-period comets arriving from the distant Oort Cloud, where an enormous population of icy bodies is thought to surround the solar system in a broad spherical reservoir. We will also consider comets that travel on open paths, including interstellar visitors that were not formed around our Sun. These objects are especially valuable because they offer direct evidence that other planetary systems also release small bodies into interstellar space. They pass through quickly. Astronomers have limited time to observe them, and the objects themselves do not slow down for interviews. Close to the Sun, there are sun-grazing comets, which approach the solar surface so closely that they face extreme heating, intense tidal forces, and a serious risk of complete destruction. Some survive, some fragment, some disappear before reaching the point of closest approach. Their paths may look dramatic in telescope images, but the physics is direct. A small body made partly of volatile material is being exposed to an environment for which it was not built. It is the astronomical equivalent of placing an ice sculpture beside an industrial furnace and hoping it has strong character. Farther out, the boundaries between comets and asteroids become less tidy. Main belt comets move through the asteroid belt on orbits that look more like those of asteroids, yet they show activity associated with escaping gas or released dust. Active asteroids can brighten, develop tails, or shed material for several reasons. Ice may sublimate, an impact may throw dust into space. Rapid rotation may loosen surface material, a body may fracture because of thermal stress. From a distance, several of these processes can produce a comet-like appearance, even when the underlying cause is different. Then there are centaurs, objects that generally travel between the orbits of the giant planets. Many are unstable over very long periods, because close encounters with those planets can alter their paths. Some centaurs become active even though they remain far from the Sun. They may contain more volatile ices, such as carbon monoxide or carbon dioxide, that can turn into gas at lower temperatures than water ice. A centaur may eventually be scattered inward and begin behaving more like a familiar short-period comet. It may also be thrown outward or removed from the solar system entirely. The giant planets do not offer a particularly secure tenancy agreement. Dormant and extinct comets add another complication. A comet does not remain visibly active forever. Each close passage around the Sun can remove material from its surface. Dust can collect and form an insulating layer. Accessible ice can become depleted. Jets may weaken. Eventually, the object may stop producing an obvious coma or tail and begin to resemble a dark asteroid. Its orbit may reveal its earlier identity even when its appearance does not. In some cases, astronomers cannot be certain whether they are looking at an asteroid, a dormant comet, or a body whose history includes characteristics of both. There are also comets known less for their orbital category than for their behaviour. Great comets become exceptionally bright and noticeable, sometimes visible during daylight or stretching tails across a large fraction of the night sky. Fragmenting comets split into pieces, occasionally producing several smaller objects that continue along related paths. Outbursting comets brighten suddenly when fresh material is exposed or gas and dust escape more rapidly. Some comets lose their tails temporarily when changes in the solar wind disturb the ionized gas around them. Others show jets, fans, spirals, or rotating patterns that reveal activity on the nucleus below. All of this begins with objects that are usually extremely dark. A comet nucleus can reflect only a small portion of the sunlight that reaches it. Up close, it may look more like charcoal than clean snow. The familiar phrase, dirty snowball, gives a rough idea of a mixture of ice and dust, but spacecraft observations have shown surfaces that are complex, rough, layered, fractured, and coated with dark material. Another description, icy dirt ball, reverses the emphasis. Neither phrase captures every comet, although both are easier to remember than irregular porous body containing refractory grains and multiple volatile compounds, which is accurate but not especially relaxing. Comets are often called leftovers from the formation of the solar system. That does not mean they have remained completely unchanged for billions of years. Their materials are ancient, but their surfaces can be altered by radiation, impacts, heating, cooling, and repeated passages near the Sun. A comet that has returned hundreds of times is not in the same condition as one arriving from a distant reservoir for the first time. The newer arrival may preserve volatile materials near its surface. The frequent visitor may have developed a crust, lost large amounts of ice, and learned, in the only sense available to a comet, to be less easily impressed by sunlight. Their origins take us back to the early solar system, when the Sun was forming inside a disk of gas and dust. Small particles collided and stuck together. Larger bodies developed. Planets formed, migrated, and scattered smaller objects through gravitational encounters. Some icy bodies remained beyond Neptune in the region, now known as the Kuiper Belt and related populations. Others were sent much farther away, possibly forming the Oort Cloud. Many were ejected entirely and became interstellar objects, wandering between stars until a chance passage brought a small number near another planetary system. That means the comet population around the Sun is connected to the history of the planets. Jupiter and the other giant planets did not simply settle into place, while everything else remained organised. Their gravity rearranged large numbers of smaller bodies. Even now, a close encounter with a planet can shorten a comet's orbit, lengthen it, redirect it, break its regular return pattern, or send it away permanently. When we classify a comet by its orbit, we're often describing the result of a long sequence of gravitational encounters rather than a path that has remained unchanged since the solar system began. The names used for comets can sound like a mixture of family records, mathematical labels, and administrative filing. Some are named after discoverers. Some carry survey names. Periodic comets receive numbers once their returning nature is confirmed. Their formal designations can include letters and numbers that tell astronomers when and how they were discovered. To a tired listener, this may appear to be the moment when astronomy becomes paperwork. Fortunately, the basic ideas are more interesting than the catalogue codes. A periodic comet is one that has been observed completing more than one trip around the Sun, or has an orbit that clearly shows it will return. The word periodic does not mean often. Halley's Comet is periodic, but most people get very few opportunities to see it. A long-period comet may technically return, but its next visit could lie thousands of years in the future. Some comets follow paths that appear hyperbolic, meaning they are not gravitationally bound to the Sun on a closed orbit. A few are clearly interstellar. Others may have started as solar system comets, and gained enough speed through gravitational interactions to escape. The difference matters because motion tells a history. The speed and direction of an object can help astronomers estimate where it came from and whether it belongs to the Sun's population. Chemical composition provides another part of the story. Spectroscopy allows researchers to identify gases and dust by studying the light a comet emits or reflects. Spacecraft provide closer views, measuring particles, mapping surfaces, and in some cases releasing an impactor or collecting material. Each method reveals something different. A telescope may show a tail millions of kilometers long. A spacecraft may reveal cliffs, pits, boulders, jets, and smooth deposits on the small nucleus responsible for the entire display. The activity begins as a comet approaches the Sun and receives more energy. Frozen materials warm and turn into gas, sometimes without passing through a liquid stage. This process is called sublimation. Gas escapes through and from the surface, carrying dust with it. The released material forms a cloud around the nucleus called the coma. Sunlight and the solar wind then act on that material, producing tails that extend away from the Sun. A comet can have a dust tail and an ion or plasma tail. The dust tail is made of small solid particles. It often appears broad and curved because the particles continue moving along related orbits, while sunlight pushes on them. The ion tail is made of electrically charged gas influenced by the solar wind and magnetic field. It generally points more directly away from the Sun. From Earth, viewing geometry can make the display look more complicated. Occasionally, a comet appears to have a tail pointing toward the Sun. This anti-tail is usually a perspective effect involving dust spread along the comet's orbital plane, not a comet forgetting the usual arrangement. The tails do not simply trail behind a comet like hair behind a runner. Their direction is controlled mainly by the Sun. When the comet moves away after its closest approach, the tails can extend ahead of its direction of travel while still pointing away from the Sun. This is one of those details that becomes obvious once explained and remains mildly confusing when seen in a diagram at midnight. Not every comet develops a spectacular tail. Activity depends on the object's composition, size, rotation, surface condition, and distance from the Sun. Some are faint and difficult to observe. Some become active beyond the orbit of Saturn. Some remain disappointing even after predictions suggest they may brighten. Comets are famous for failing to follow publicity schedules. An object can be announced as a possible naked-eye spectacle, and then remain visible mainly to people with excellent telescopes, dark skies, and a generous interpretation of the word spectacle. Others exceed expectations. A new comet may brighten rapidly as fresh ice becomes exposed. It may produce a large coma and a tail visible from cities. Historical observers often treated such appearances as signs or warnings because comets didn't resemble the regular movements of the planets and stars. They arrived unexpectedly, changed shape and disappeared. Today, we understand much more about their orbits and physical behaviour, but surprise has not been removed from comet science. A newly discovered object can still force astronomers to revise predictions as more observations refine its path and activity. The unpredictability comes partly from the nucleus itself. It is small, rotating, irregular, and often hidden inside the coma. Jets can turn on and off as different regions receive sunlight. A crust may crack, a cliff may collapse, a pocket of volatile material may become exposed. The nucleus may spin faster as escaping gas produces torque. If rotation becomes too rapid, pieces can separate. If internal stresses become too large, the body can split. Predicting the brightness of a comet is therefore not like predicting the phase of the moon. It is more like predicting how an old freezer full of dust will behave after being pushed toward a furnace while rotating through space. The mathematics helps, but the freezer has opinions. There is another reason comets are worth studying. They preserve information about conditions that existed when planets were forming. Their ices and dust contain chemical clues. Measurements of water, carbon-bearing compounds, noble gases, and organic molecules help researchers compare different formation regions and test ideas about how material moved through the early solar system. Comets may also have delivered some water and organic material to the early Earth, although the size of their contribution remains a subject of research. They were not necessarily responsible for filling every ocean, and they should probably not be given sole credit for tea. Studying different comet types allows those clues to be sorted more carefully. A Jupiter family comet has lived through a different recent history, from a long-period comet making an early passage through the inner solar system. An interstellar comet formed around another star, and may reflect a different planetary environment. A main belt comet may preserve ice in a region once assumed to be dominated by rock. A dormant comet may reveal how active objects change as their accessible volatiles are exhausted or sealed beneath surface layers. The classifications are tools, not rigid boxes. Nature often produces objects that sit near boundaries. Orbit-based categories can change after close planetary encounters. Activity-based labels can change as surfaces evolve. New observations can reveal that an object placed in one group behaves more like another. The phrase, "every comet type," therefore does not mean that the universe has provided a finished menu with a fixed number of entries. It means we will examine the main categories astronomers currently use, the reasons those categories exist, the cases that blur them, and the physical processes that connect one group to another. That last point is important because a single object can move through several identities over time. An icy body beyond Neptune may be disturbed into an orbit that crosses those of the giant planets. It may spend time as a centaur. Further encounters may send it inward, where it becomes a short-period comet. Repeated heating may reduce its activity until it looks like a dormant comet. A collision or rotational breakup may fragment it. Eventually it may strike a planet, fall into the Sun, break into smaller debris, or be ejected into interstellar space. From our viewpoint, we tend to meet a comet during one brief stage of that long process. We see it brighten, measure its orbit, photograph its tail, and assign it a name. The object may have spent billions of years in darkness before that discovery. It may remain observable for only a few months. The contrast is striking, but there is no need to make it mysterious. Most of a comet's orbit is simply far away, cold and faint. It becomes visible when sunlight gives us something to detect. For tonight, that gradual change will guide us. We will begin with the basic physical definition before separating the orbital families and unusual behaviours. We will look at what is actually inside a comet, why activity begins, why tails form, and why a dark nucleus can produce something bright enough to be seen across enormous distances. Once that foundation is in place, the different types become easier to understand. Their names stop feeling like disconnected labels and begin to describe where they came from, how they move, and what the sun does to them. So, settle into whatever position is comfortable. Let the room remain quiet. There is no need to memorize every term, orbital period, or chemical process. Comets themselves take a long time to complete most of what they do, and we can afford to proceed at a reasonable pace. If you find this kind of calm scientific journey useful, you may like the video, subscribe to the channel, or share it with someone who also enjoys learning without being shouted at. It helps Science for Sleep reach more listeners and allows this quiet part of the internet to continue examining large subjects at a volume suitable for bedtime. For now, picture a small object moving in the outer solar system. It is dark enough to be difficult to see, cold enough for several gases to remain frozen, and far enough from the sun that nothing resembling a familiar tail surrounds it. At this distance, it may not look like a comet at all. It is simply a nucleus following an orbit. As it moves inward, sunlight grows stronger, parts of the surface warm, gas begins to escape, dust lifts away. A coma develops around the nucleus, and the object changes from an almost invisible body into the form we recognize. What exactly must an object do before astronomers call it a comet? The simple answer is that a comet is a small body containing volatile material that releases gas and dust when it is warmed. Most comets orbit a star, and in our solar system that star is the Sun. The solid object at the centre is called the nucleus. When the nucleus becomes active, it can produce a cloud called a coma and, under the right conditions, one or more tails. This definition sounds neat, which is usually a warning that nature will soon make it untidy. A frozen body far from the sun may show no visible activity at all. It may look like a faint point of light, much like an asteroid. The same object can later move inward, begin releasing gas, surround itself with dust, and become unmistakably comet-like. Its identity has not suddenly changed because someone switched on a tail. The materials and orbit were already there. What changed was the amount of solar energy reaching the surface. At the centre of the whole display is the nucleus. This is the permanent solid body, although permanent is a generous word for something that can crack, erode, split, and slowly lose mass on every close approach to the sun. A typical nucleus is only a few kilometres across, though known examples cover a wider range. It is made from a mixture of non-volatile grains and frozen compounds. Water ice is common, but comets also contain carbon dioxide, carbon monoxide, methane, ammonia, and other substances that can remain frozen at low temperatures. The word ice can be misleading because it may suggest a clean block of frozen water. An actual comet nucleus is much darker, rougher, and more complicated. Dust, minerals, and carbon-rich material can cover the surface. Spacecraft images show cliffs, pits, fractures, boulders, smooth deposits, and areas that look as though several different landscapes were pressed onto one small object. Many comet nuclei reflect only a small fraction of the sunlight that strikes them. A comet can produce a bright coma, while its nucleus remains darker than a freshly paved road, which is one reason the nucleus is so difficult to observe from Earth. The old description of a comet as a dirty snowball is still useful as a first approximation. It tells us that ice and solid grains are mixed together. It does not tell us how porous the body may be, how much dust it contains, or how its layers are arranged. Measurements of Comet 67P by the Rosetta mission showed a low-density, highly porous nucleus. The object was not a solid lump of ice, with a little dust sprinkled through it. It behaved more like a fragile mixture of ice and dusty material, with a great deal of empty space on small scales. In household terms, it was closer to a badly made frozen sponge than a large ice cube, although putting either one in a spacecraft would cause paperwork. A comet nucleus also has very weak gravity. You would not stand firmly on the surface in the way you stand on Earth. A small push could send material drifting away, especially once gas begins escaping. Dust grains can be lifted from the surface and carried outward by flowing gas. Larger pieces may tumble nearby or fall back. The low gravity helps a comet create a large cloud from a relatively small body, but the gas still needs a source of energy. That source is mainly sunlight. As the comet moves closer to the sun, its surface absorbs more solar radiation. The temperature rises, although not evenly. The sunlit side warms more than the dark side. Rotation brings different areas into daylight. Slopes receive sunlight at different angles. Dust layers insulate some regions, while exposed ice responds more quickly. Heat can also travel below the surface, reaching volatile material buried beneath a crust. The result is not a smooth, even release of gas from the entire nucleus. Activity often comes from particular regions, cracks, pits, or patches. When a frozen substance changes directly into gas without becoming liquid first, the process is called sublimation. On Earth, dry ice provides a familiar example. Solid carbon dioxide turns into gas and produces the low fog often used in stage effects and school demonstrations. On a comet, sublimation can occur with water ice and with more volatile compounds. The gas expands into the near vacuum around the nucleus. As it escapes, it can pull loose dust and small grains from the surface. Water usually becomes the main driver of activity when a comet is close enough to the sun, but it is not the only option. At greater distances, the nucleus may still be too cold for strong water ice sublimation. Carbon monoxide and carbon dioxide can become active at lower temperatures. This helps explain why some comets develop comas while they are still far beyond the region where water would be expected to do most of the work. The phrase frozen and inactive therefore does not apply at one universal distance. Composition matters, and comets rarely submit a complete ingredient list before observation begins. The escaping material can emerge in broad flows, but it often forms jets. A jet is a more concentrated stream of gas and dust coming from an active region. Because the nucleus rotates, the direction of a jet changes with time. Long exposure images can show fans, arcs, shells, or spiral patterns in the surrounding coma. By following those patterns, astronomers can estimate how fast the nucleus rotates and where active areas may be located. A rotating comet with several jets can resemble a garden sprinkler operating in very slow motion, except the garden is empty space and the sprinkler may be 4 kilometers wide. Jets can also affect the rotation itself. Escaping gas produces a small reaction force on the nucleus. The effect is tiny at any one moment, but it can continue for weeks or months. Depending on where the active regions are located, outgassing can speed up the rotation, slow it down, or alter the direction of the spin axis. These forces can also cause slight changes in the comet's orbit. Astronomers call them non-gravitational forces because they are not produced by the gravity of the Sun or planets. The name sounds as though the comet has stopped respecting physics, but it simply means that gas is acting like a weak natural thruster. Once gas and dust surround the nucleus, the comet has developed a coma. This is a temporary atmosphere, though it is unlike the stable atmosphere around a planet. It is constantly supplied by the nucleus and constantly lost to space. There is no strong gravity to hold it in place. Material flows outward, sunlight changes the gas chemically, and the solar wind carries charged particles away. The coma may grow to tens or hundreds of thousands of kilometers across, making the visible head of the comet much larger than the solid body hidden inside it. That difference in scale is worth holding in mind. A nucleus may be comparable in size to a town, while its coma can become wider than a planet. This does not mean the coma contains more material than a planet, or that it would feel like a thick cloud if you travelled through it. It is extremely thin. The particles and molecules are spread through a very large volume. A spacecraft can pass through a coma without encountering anything like atmospheric pressure at Earth's surface, although dust grains can still be a concern when the spacecraft is moving quickly. The coma becomes visible in more than one way. Dust reflects sunlight. Gas molecules absorb solar radiation and then emit light at particular wavelengths, a process that allows astronomers to identify chemical species with spectroscopy. Different filters and instruments reveal different parts of the coma. A visible image may emphasize dust. Ultraviolet observations can detect hydrogen and other products created when sunlight breaks larger molecules apart. Radio and infrared instruments can measure molecules that are difficult to study in visible light. Surrounding some comets is an enormous cloud of hydrogen, produced after water molecules are released and broken apart by solar ultraviolet radiation. This hydrogen envelope can be much larger than the visible coma. Human eyes cannot simply look up and see it. Much of its radiation is blocked by Earth's atmosphere, so spacecraft observations are especially useful. A comet, therefore, has structures that extend far beyond the bright shape shown in ordinary photographs. What we see from the ground is only part of the activity. The tail begins when material from the coma is pushed away from the Sun. It is common to speak of a comet's tail as though it were one object streaming behind the nucleus, but active comets generally produce at least two main kinds. The dust tail contains solid particles. The ion tail contains electrically charged gas. They respond to different forces, so they have different shapes and directions. Dust grains leave the nucleus with the escaping gas, but once they are in space, sunlight affects them. Photons carry momentum, and the pressure of sunlight gradually pushes small grains away from the Sun. The grains also continue moving under solar gravity and retain some of the orbital motion they had when they left the nucleus. This combination produces a broad tail that is often curved. Larger grains respond differently from smaller grains, so the dust can spread into separate structures. A bright dust tail may look smooth from a distance, while containing material released at different times and speeds. The ion tail forms through a different process. Ultraviolet radiation from the Sun removes electrons from gas molecules, producing ions. These charged particles interact with the solar wind and the magnetic field carried through interplanetary space. The ion tail is usually narrower and straighter than the dust tail, and it points almost directly away from the Sun. Changes in the solar wind can create knots, waves, or sudden breaks. At times, a comet can appear to lose part of its ion tail when a disturbance in the solar wind disconnects it. The comet has not misplaced the tail permanently. New ionized material continues to flow outward and forms another one. Because the Sun controls the direction of the tails, they do not always trail behind the comet's motion. Before the comet passes its closest point to the Sun, the tails extend generally behind the sunward direction. After the comet swings around and begins travelling outward, the tails still point away from the Sun. That can place them ahead of the nucleus along its path. A comet is therefore capable of moving tail first without feeling the slightest embarrassment. An anti-tail can make the geometry look even stranger. This feature appears to point toward the Sun, but it is not a true tail being driven in the wrong direction. Dust released from the comet spreads along its orbital plane. When Earth passes through or near that plane, perspective can make part of the dust sheet look like a narrow feature extending sunward. It is similar to looking along the edge of a thin sheet of paper. The sheet appears as a line because of the viewing angle. Not every active comet displays all of these features clearly. A weak comet may show only a small coma. A dust-rich comet can produce a prominent dust tail while the ion tail remains difficult to photograph. Geometry can hide or shorten one feature. Moonlight, city lighting, atmospheric conditions, and the comet's position in the sky affect what observers can see. Images made with different exposure times may also present very different versions of the same object. The grand photograph and the faint grey smudge in a small telescope can both be accurate, which is comforting after someone has driven to a dark field at 2 a.m. Brightness alone does not define a comet. Some comets are spectacular, but many are extremely faint. Nor does a tail define one. A nucleus far from the Sun can still be a comet even when no tail is present. More importantly, comet-like activity can appear on objects whose orbits resemble those of asteroids. This is where the apparently simple distinction between rocky asteroids and icy comets begins to fail. Traditionally, asteroids were described as mostly rocky or metallic bodies, while comets were described as ice-rich bodies that developed comas and tails. The broad distinction remains useful, but observations have revealed active asteroids, main belt comets, dormant comets, and transitional objects. Some asteroid-like bodies release dust because ice is sublimating. Others release dust after impacts, rotational breakup, or thermal cracking. A visible tail therefore proves that material is leaving the object, but it does not automatically prove that sublimation is responsible. Astronomers look for several clues. Repeated activity near the same part of an orbit suggests solar heating may be exposing or warming ice. Detection of gas provides stronger evidence of cometary activity. A dust cloud that appears immediately after an impact may be explained without sublimation. The orbit also matters. A body moving on a typical cometary path may be a dormant or weakly active comet, even when no gas is detected. No single clue solves every case, so classification often combines physical observations with orbital history. This is why an inactive comet nucleus and an asteroid can be difficult to distinguish in a telescope image. Both may appear as unresolved points. Both can be dark. Both can occupy overlapping size ranges. The difference may become clear only when the object approaches the Sun, when precise tracking reveals a small acceleration caused by outgassing, or when infrared and spectroscopic measurements show the presence of volatile material. Occasionally, an object spends years in an asteroid catalogue before faint activity is detected. The object has not been deceiving anyone intentionally, it has simply been economical with visible evidence. Dormant and extinct comets extend the problem further. A dormant comet still contains volatile material, but its activity is weak or blocked. A layer of dust may insulate the ice. Active regions may cover only a tiny portion of the surface. An extinct comet has lost most of the accessible volatile material needed to drive obvious activity. In practice, proving that every usable pocket of ice is gone is difficult, so the labels describe levels of activity and likely history rather than a perfectly measurable boundary. Each trip near the Sun changes the nucleus. Sublimation removes ice. Gas carries dust away. Some dust falls back and forms a surface layer. Cracks open and close as temperatures change. Cliffs collapse. Pits expand. The shape and rotation can evolve. A comet that has made many close approaches may develop a thick, processed surface that behaves differently from the fresher material below. It can remain quiet for a time, and then brighten when a collapse or fracture exposes a new source of ice. Sudden brightening is called an outburst. The exact cause can vary. Pressure may build below the surface. A fragile area may fail. A previously shadowed region may receive sunlight. A chunk may break away and expose fresh material. Outbursts can increase the amount of gas and dust dramatically over a short period. They are another reason comet brightness is hard to predict. An orbit can be calculated with high precision, while the activity of the nucleus remains much less cooperative. Fragmentation is a more severe change. The nucleus may split because of thermal stress, rapid rotation, internal weakness, tidal forces during a close approach to a massive body, or a combination of effects. The pieces can remain near one another for a while, each producing its own coma. Some fragments survive, others fade or disintegrate into smaller debris. Material left along the orbit can later intersect Earth's path, and create a meteor shower when the grains enter our atmosphere. This connection between comets and meteor showers gives us another way to recognize their influence. A meteor is the streak of light produced when a small particle enters an atmosphere at high speed. Many annual meteor showers occur when Earth passes through streams of dust released by comets on earlier orbits. The comet itself does not need to be nearby at the time. It may be elsewhere in the solar system while its old dust produces brief flashes above us. The nucleus, coma, tail, and meteor stream are therefore different parts of a longer process of material loss. Space missions have made the physical definition of a comet much clearer, while also making the category more complicated. Before spacecraft reached these objects, astronomers could study their light, motion, gas, and dust, but the nucleus was usually hidden by the coma. Close images revealed irregular dark bodies rather than bright white snowballs. Missions have flown past comets, orbited one, landed on one, struck one with an impactor, and returned dust samples to Earth. Every visit has shown that comets are active geological bodies, even though their geology is driven by weak gravity, volatile ice, and repeated heating rather than by the familiar processes shaping Earth. This Stardust mission returned particles from Comet Wild 2. Rosetta followed Comet 67P for about 2 years as it approached and passed the Sun, while the Philae lander made measurements on the surface. Deep Impact released an impactor into Comet Tempel 1 to expose subsurface material. These missions found minerals, organic compounds, gases, and complex dust. They also showed that material inside a comet can include grains formed under very different temperature conditions, evidence that matter moved through the young solar system before being incorporated into comet nuclei. Calling comets leftovers from planetary formation is accurate, but it should not make them sound like untouched museum samples. Their ingredients are ancient, their present surfaces are processed. Radiation alters materials during long periods far from the Sun. Impacts create damage. Repeated close approaches remove layers and rearrange dust. A newly arriving long-period comet may preserve different accessible materials from a short-period comet that has been heated many times. Comparing them helps researchers separate early formation history from later evolution. There is also no requirement that a comet belong permanently to one environment. Gravitational encounters can move objects from distant reservoirs into shorter orbits. The giant planets can redirect them. Activity can weaken. A nucleus can fragment. An object may eventually collide with a planet or the Sun, or it may be ejected from the solar system. The word comet describes a physical kind of small body and its capacity for volatile-driven activity, but the object's appearance and orbit can change greatly during its lifetime. So, what makes a comet a comet? It is not simply the tail, because a comet can have no visible tail. It is not brightness, because most are faint. It is not a perfect list of ingredients, because compositions vary and are difficult to measure completely. The most useful answer is that a comet is a small body containing ice and dust, whose volatile materials can become active, producing gas and often carrying solid particles into space. The coma and tails are temporary results of that activity. The nucleus is the source. A short-period comet is generally defined as a comet that takes less than 200 years to complete one orbit around the Sun. That is short only by astronomical standards. A person waiting 190 years for a comet to return might reasonably object to the description. The category includes objects that circle the Sun every few years, as well as those that need several human lifetimes to complete the trip. Within that broad group are two main populations. Jupiter family comets usually have orbital periods of less than 20 years and paths strongly influenced by Jupiter. Halley-type comets generally take between 20 and 200 years to return and often travel on more steeply tilted orbits. We will meet those longer period returners soon. For now, the more frequent visitors deserve our attention. because astronomers can observe the same objects again and again, watching how they change after repeated exposure to the Sun. Jupiter family comets are not moons of Jupiter, and they do not spend their entire lives circling the giant planet. They orbit the Sun. The family name describes the important role Jupiter's gravity plays in shaping their orbits. Most travel from the inner solar system to a region near Jupiter's orbit and then come back again. Their paths are usually prograde, meaning they move around the Sun in the same general direction as the planets. Many also have relatively low orbital inclinations, so they remain closer to the broad plane in which most planets travel. Their present arrangement is the result of a long gravitational journey. Most Jupiter family comets are thought to trace their origins to icy populations beyond Neptune. Many begin in the Kuiper belt, or, more precisely in numerous cases, in the scattered disk, a broader region containing objects placed on stretched and tilted orbits by past interactions with Neptune. An object living beyond Neptune can remain there for a very long time. It receives little solar warmth, moves slowly along its distant orbit, and may show no activity that could be detected from Earth. A gravitational disturbance can gradually change that situation. It may pass near Neptune, and the encounter can alter its orbit. It may then begin crossing the paths of other giant planets. Uranus and Saturn can make further adjustments. Eventually, it may reach a path that brings it close to Jupiter. This process does not usually happen in one clean movement. The object may undergo many encounters spread across thousands or millions of years. Each encounter changes its speed or direction by a small or substantial amount. The giant planets act less like orderly traffic officers and more like several people repeatedly redirecting a shopping trolley in a large car park. The trolley may eventually reach the entrance, but its route will not be elegant. Jupiter is especially effective because it is the most massive planet in the solar system. Its gravitational influence extends far beyond the visible clouds surrounding it. When a comet passes near Jupiter, the planet can exchange energy and angular momentum with the smaller body. Depending on the geometry of the encounter, the comet may leave with a shorter orbit, a longer orbit, or a path that sends it away from the solar system entirely. A successful capture into a Jupiter family orbit does not mean the comet is trapped in a perfectly stable loop forever. The orbit can continue to evolve. Repeated approaches to Jupiter may alter the timing and distance of future passages. Encounters with the other planets can add smaller changes. Outgassing from the comet itself creates weak forces that gradually modify its motion. Astronomers can calculate these effects, but long-term predictions become increasingly uncertain as repeated encounters accumulate. The classical definition of a Jupiter family comet is straightforward. It has an orbital period shorter than about 20 years, and Jupiter has had a major role in shaping its orbit. Astronomers also use a mathematical quantity called the Tisserand parameter with respect to Jupiter. This combines several features of an orbit, including its size, shape, and inclination. The full calculation is useful to specialists, but the basic purpose is easy to understand. The Tisserand parameter helps researchers compare the motion of an object with the orbit of Jupiter. Most Jupiter family comets have values between roughly 2 and 3. Most ordinary main belt asteroids have larger values. The boundary is not perfect, because some asteroids move on comet-like orbits, and some comet-related objects fall outside the usual range. It is a guide rather than a security gate staffed by Jupiter. A short orbital period makes these comets predictable. Once astronomers have measured a comet's orbit carefully, they can calculate when it will return to the inner solar system. The predicted position can be refined after every appearance. Observers know where to aim their telescopes, spacecraft planners can evaluate possible missions, and scientists can compare the comet's activity from one return to the next. Predictable does not mean visually reliable. The orbit may be known well, but the brightness can still be difficult to forecast. One return may expose a fresh patch of ice and produce stronger activity. Another may be quieter, because dust has covered the active region. A sudden outburst can make the comet brighten. Fragmentation can alter the display completely. The date of arrival may be dependable while the performance remains open to negotiation. Their repeated passages near the Sun make Jupiter family comets especially useful for studying comet evolution. Each time one approaches the inner solar system, its surface warms. Ice sublimates, gas escapes, and dust is lifted into the coma and tails. Some material falls back onto the nucleus, some is lost permanently. Cracks widen, cliffs collapse, and active areas shift. Over many orbits, the comet becomes increasingly processed. The easily reached volatile material near the surface may be depleted. Dust that cannot escape can form a dark insulating layer. Activity may become confined to small areas where fractures expose buried ice. The comet can grow less active, even though its orbit continues to bring it close to the Sun. This gives Jupiter family comets comparatively short active lifetimes. Short does not necessarily mean a few years. They may remain active for thousands of years and complete hundreds or thousands of returns. That is still brief compared with the age of the solar system. A body can spend billions of years stored in the cold outer regions and then use up much of its accessible volatile material during a relatively short period of frequent visits. The final condition is not always complete destruction. Some nuclei split into pieces, some collide with the Sun or a planet. Jupiter can eject some after a close encounter. Others become dormant or nearly extinct, continuing to follow comet-like orbits without producing an obvious coma. They may then be catalogued as asteroid-like objects, until further observations reveal signs of their earlier nature. This fading process explains why astronomers suspect that some near-Earth asteroids are actually inactive comet nuclei. Their orbits resemble those of comets, and their dark surfaces may be consistent with heavily processed cometary material. Without visible gas or dust, certainty can be difficult. An exhausted comet and a naturally dark asteroid can look very similar when both appear as small points of light. Among the best-known frequent returners is Comet 67P/Churyumov-Gerasimenko. It completes an orbit in about 6.5 years. Its path takes it from a point slightly beyond Jupiter's orbit to a position between the orbits of Earth and Mars. This regular return made it a practical target for the European Space Agency's Rosetta mission, although reaching it was still far from simple. Rosetta launched in 2004 and spent roughly a decade travelling through the solar system. It used gravitational encounters with the Earth and Mars to adjust its speed and path before meeting the comet in 2014. Rather than making a brief flyby, Rosetta matched the comet's motion and travelled with it. The spacecraft observed 67P while it was relatively quiet, watched it become increasingly active as it approached the Sun, and continued studying it as it moved outward again. Close images revealed a nucleus with 2 distinct lobes joined by a narrow region. People compared it with a rubber duck, which is one of the kinder descriptions ever given to a dark object several kilometres wide. The shape may have formed when 2 smaller bodies collided gently and remained joined, although scientists have examined several possible formation histories. The surface was far more varied than a simple frozen lump. Rosetta saw cliffs, pits, fractures, boulders, smooth plains, dusty deposits, and regions where jets emerged as sunlight reached active material. The mission measured gases and dust, monitored changes in rotation, and observed the erosion caused by activity. It gave researchers an extended view of how a Jupiter family comet behaves through a large part of its orbit. The Philae lander separated from Rosetta and descended toward the nucleus in November 2014. Its anchoring systems did not work as planned, and the lander bounced across the surface before settling in a shadowed position. This was not the intended arrival, but it was an impressive demonstration of how slowly events can unfold in weak gravity. Philae made measurements before its batteries were exhausted, while Rosetta continued the main investigation from nearby. Repeated heating has shaped 67P, but its 6.5-year orbit has not remained constant throughout its history. A close encounter with Jupiter in 1959 moved its perihelion, the closest point to the Sun, substantially inward. Before that encounter, it did not approach the Sun as closely and would have received less heating. The comet observed by Rosetta was therefore living on an orbit partly created by a relatively recent meeting with Jupiter. Comet 9P/Tempel 1 offers another example. It completes one orbit in about 5.5 years. NASA's Deep Impact mission reached it in 2005 and released a copper impactor into the nucleus. The collision excavated material from below the processed surface, while the main spacecraft observed the result. The impact produced a large cloud of dust that initially obscured the crater. This was scientifically inconvenient, but entirely appropriate for a mission called Deep Impact. Researchers studied the released material to learn about the comet's composition and internal structure. 6 years later, the Stardust Next spacecraft flew past Tempel 1 and photographed the region again, giving scientists an opportunity to examine the surface after another passage around the Sun. Tempel 1 shows why returning to the same comet matters. A single observation provides a snapshot. Repeated visits reveal change. Researchers can compare activity levels, surface features, rotation, and material loss. Jupiter family comets are not static samples kept in cold storage. Once they enter short-period orbits, they become evolving bodies whose surfaces are modified each time they approach the Sun. Comet 103P/Hartley-2 returns about every 6.5 years and has a nucleus roughly 1.5 kilometers wide. NASA's epoxy mission flew past it in 2010. Images showed an elongated object with a narrow central region and active ends. Jets carried material away from the nucleus, including chunks of ice. Hartley 2 was unusually active for its small size. Carbon dioxide escaping from parts of the surface helped lift water-ice particles into the coma. Some of the water detected around the comet therefore came from icy grains outside the nucleus, rather than directly from water vapor leaving the surface. This made its activity more complicated than a simple picture in which sunlight warms exposed water ice evenly. A small nucleus can support a surprisingly large coma when volatile-driven jets efficiently release material. Hartley 2 demonstrates that the size of the nucleus does not alone determine how impressive a comet becomes. Composition, active surface area, rotation, and the distribution of different ices all contribute. A larger comet with a heavily sealed surface may be less active than a smaller one with exposed volatile material. Comet 19P/Borrelli has a period of about 7 years. The Deep Space One spacecraft flew past it in 2001 and photographed an elongated nucleus with strong activity concentrated in particular areas. Much of its surface appeared inactive. A limited region produced a major jet, showing again that a comet does not need to release material evenly from every part of its surface. Borrelli's orbit carries it from inside the orbit of Mars to beyond Jupiter. Like other members of the family, it moves between a warm inner region where activity becomes strong and a colder outer region where the coma weakens. From Earth, it may seem to switch on and off, but the change is gradual. Gas and dust production rises as it approaches the Sun and falls after it moves away. Comet 2P/Encke is an especially interesting short-period object. It takes only about 3.3 years to orbit the Sun, the shortest known period of any recognized comet in our solar system. Its path remains mostly inside Jupiter's orbit. Under the simplest period-based definition, it is often discussed alongside Jupiter family comets. More detailed dynamical systems may place it in an Encke-type group because its relationship with Jupiter differs from that of a typical Jupiter family member. This is a useful reminder that classification depends on the question being asked. Someone describing observable return times may call Encke a short-period comet and include it in a broad discussion of frequent visitors. Someone studying orbital dynamics may separate it because its Tisserand parameter and orbit do not fit the standard Jupiter family range. Both approaches can be valid when their definitions are stated clearly. Encke's frequent returns have strongly processed its surface. It produces less dramatic displays than some newer comets, but it has supplied a large stream of dust through repeated activity. Earth passes through parts of this material, producing the torrid meteor showers. The broader torrid complex may include debris released over a long period, possibly involving fragmentation and more than one related object. Meteor streams provide a record of repeated comet activity. Every close passage can release dust that spreads gradually around the orbit. The nucleus moves on, but the grains remain. Over time, planetary gravity and radiation pressure alter the distribution. When Earth crosses the stream, particles enter the atmosphere and create meteors. Some Jupiter family comets are parents of familiar annual showers. Comet 21P/Giacobini-Zinner supplies the Draconids, while Comet 55P/Tempel-Tuttle, which belongs to the Halley type group rather than the Jupiter family, produces the Leonids. The differences between those parents help explain why meteor showers can behave differently. A compact trail left by a recent passage can produce a sudden storm, while a broad, older stream may create a more modest display each year. Frequent returners can also pass close to planets. Most encounters are distant enough to cause only orbital adjustments, but rare collisions occur. The most famous modern example involved Comet Shoemaker-Levy 9. It was probably a Jupiter family comet before becoming temporarily captured by Jupiter. A close approach in 1992 pulled the nucleus apart into a chain of fragments. Those pieces struck Jupiter in July 1994. The impacts produced enormous dark marks in Jupiter's atmosphere. Telescopes around the world observed the event, and spacecraft gathered additional measurements. It was the first time astronomers directly watched two solar system bodies collide on such a scale. The event also showed what Jupiter does besides reshaping orbits. Its gravity can capture, tear apart, and absorb comets. Calling Jupiter a protective shield for Earth is too simple. The planet can remove some potentially dangerous objects by capturing them or throwing them out of the solar system. It can also redirect objects toward the inner planets. The effect depends on the original orbit and the details of the encounter. Jupiter is better described as a major gravitational organizer whose work occasionally resembles cleaning and occasionally resembles throwing the contents of a cupboard across the kitchen. The possibility of an impact is one reason astronomers track short-period comets carefully. Because these objects return repeatedly, their orbits can be refined over long periods. Most do not threaten Earth. Even when a comet crosses Earth's orbital distance from the Sun, the two objects usually reach the crossing point at different times. An orbit crossing is not automatically a collision course. Outgassing adds a complication. Jets produce small changes that can accumulate. Close planetary encounters introduce larger uncertainties. Fragmentation can create new bodies whose paths must be measured separately. Continued observation is therefore important, particularly for comets that enter the near-Earth region. Their accessibility has made Jupiter family comets popular spacecraft targets. A mission to a long-period comet may have limited warning because the object can be discovered only after it has begun moving into the inner solar system. Its orbit may also be highly inclined, fast, and difficult to reach. A known Jupiter family comet returns on a schedule. Engineers can plan years in advance, although the mission may still require gravity assists and a route that looks suspiciously indirect on a diagram. The targets are also scientifically useful because they represent material from the outer solar system that has undergone repeated heating. Missions can study both ancient ingredients and recent changes. By comparing several Jupiter family comets, researchers can ask whether their different shapes and activity patterns reflect original formation conditions, later evolution, or both. No two observed nuclei have looked exactly alike. Some are elongated, some appear to have two lobes. Surfaces vary in roughness, layering, dust cover and active regions, and densities measured for several nuclei indicate porous structures. Their weak internal strength helps explain why splitting and surface collapse can occur. The two-lobed shapes seen on objects such as 67P and Hartley, too, may indicate gentle mergers between smaller bodies. Another possibility is that erosion narrowed a previously larger central region. Different comets may have reached similar shapes through different processes. A familiar outline does not guarantee an identical history, just as two potatoes can look alike without sharing a childhood. Rotation also varies. Some nuclei turn in a matter of hours. Others rotate more slowly or have complex spin states. Jets can change the rotation period, and fragmentation can occur if the spin becomes too rapid for the weak structure to hold together. Scientists monitor brightness variations and coma patterns to estimate rotation when direct images are unavailable. A Jupiter family comet is therefore not defined by one appearance. It may be bright or faint, large or small, dust-rich or gas-rich, strongly active or nearly dormant. What connects the group is primarily orbital history. These are icy bodies moved inward from colder populations, placed on relatively short paths and repeatedly influenced by Jupiter. Their familiarity is limited. We can know when they are due without fully knowing what condition they will be in. Every return removes material and creates new surfaces. A comet observed now may look different when it comes back several years later. After enough passages, it may no longer produce a visible display at all. That gradual fading makes the frequent returners useful for understanding the later stages of comet life. They allow astronomers to watch the transition from active comet to weakly active body, fragmented object, or dormant nucleus. Their paths also show that comet categories are not fixed from the moment of formation. A body can begin beyond Neptune, become a centaur, enter the Jupiter family, lose its activity, and later be ejected or destroyed. Halley-type comets belong to the short-period population because they complete an orbit in less than 200 years, yet they differ clearly from the frequent visitors controlled more closely by Jupiter. Under the classical definition, a Halley-type comet takes between 20 and 200 years to travel around the Sun. It may return several times within the span of recorded history, but usually not often enough for one person to see more than one appearance. The name comes from the most famous member of the group, Comet 1P/Halley. It takes roughly 76 years to complete an orbit, although the exact interval changes because the planets disturb its path. Its measured periods between returns have varied by several years. Jupiter and Saturn can slightly accelerate or delay it, which means even a comet famous for keeping an appointment does not arrive according to a perfectly fixed timetable. It is more reliable than a bus, but it has the benefit of several decades in which to correct the schedule. Halley-type comets generally follow more elongated orbits than Jupiter family comets. They spend most of their time far from the Sun and then move rapidly through the inner solar system. Many approach from steep angles relative to the plane of the planets. Some orbit in the opposite direction, a motion called retrograde. Their varied inclination suggests a different history from the flatter, mostly prograde Jupiter family population. That difference points toward the Oort Cloud. The leading explanation is that many Halley-type comets began in this distant, roughly spherical reservoir of icy bodies surrounding the solar system. Objects in the Oort Cloud can approach the Sun from almost any direction because they do not occupy one narrow shared plane. Most disturbed objects enter extremely long orbits, but repeated gravitational encounters can gradually reduce the orbital periods of a small number. Those altered bodies may eventually settle into Halley-type paths. The details are difficult to reconstruct. A comet may have experienced numerous encounters with the giant planets before reaching the orbit observed today. Each pass can change its speed, direction, and orbital period. After many returns, the original route is no longer obvious. Astronomers can work backward using computer simulations, but small uncertainties grow over time. The farther they attempt to trace the comet into the past, the more possible histories appear. This is especially true for Halley itself. Its current orbit crosses a large range of the solar system, carrying it from inside the orbit of Venus to a point beyond Neptune. It travels retrograde, moving around the Sun in the direction opposite to the planets. Its orbital plane is strongly tilted when described in the usual way, giving the comet a high-speed encounter with the inner planetary region each time it returns. These features are unusual among familiar short-period comets, and are more consistent with a body whose earlier history involved the Oort Cloud. Orbital period is the simplest way to identify the group, but astronomers also use the Tisserand parameter relative to Jupiter. Most Halley-type comets have values below about 2, while Jupiter family comets usually lie between about 2 and 3. The parameter combines the shape, size, and inclination of an orbit into one useful quantity. It helps distinguish objects that may have similar periods but different dynamical relationships with Jupiter. The categories do not meet along a perfectly clean line. A comet with a period slightly below 20 years may move on an orbit that behaves more like that of a Halley-type comet. Another body may fit the period range but have unusual dynamical properties. The classical period definition remains convenient, while more detailed research often considers the orbit as a whole. The comet does not know which system is being used and continues around the Sun without updating the form. The long interval between returns affects how these objects are observed. A Jupiter family comet may appear every 5 or 6 years, allowing several groups of astronomers to compare consecutive visits. A Halley-type comet can disappear for decades. Instruments improve, observatories close, new ones are built, and generations of researchers change before the nucleus comes back. This creates a scientific challenge. Observations from an earlier return may have been made with technology that now seems limited. Drawings may replace photographs. Written descriptions may use older measurement systems. Brightness estimates may vary between observers. By the next return, astronomers can gather much more precise data, but they cannot go back and repeat the previous observation with modern instruments. At the same time, these long gaps give us a record of human history. Some Halley-type comets have been seen repeatedly for centuries. Their appearances connect observers who understood the sky in very different ways. A comet recorded as an omen by one society may later be recognized as the same object moving on a calculable orbit. What changed was not the comet's intention. What changed was our ability to compare records and explain its motion. Halley's comet provides the clearest example. Confirmed records of its appearances extend back more than 2,000 years. Chinese observers recorded it in 240 BCE, and possible earlier sightings have also been discussed. Later descriptions appear in records from several parts of the world. The comet returned again and again, but for most of that history, each appearance was treated as a separate visitor. Its appearance in 1066 became especially famous because it was shown in the Bayeux Tapestry. People in England associated the comet with the political crisis surrounding the Norman invasion and the Battle of Hastings. Some viewed it as a warning, while William of Normandy reportedly regarded it more favourably. Celestial interpretation has always depended partly on which side expects to win. The major change came in the late 17th and early 18th centuries. Edmund Halley studied observations of comets seen in 1531, 1607, and 1682. Using Newton's new description of gravity and motion, he concluded that these were not 3 separate comets. They were repeated appearances of the same object. Halley predicted that it would return around 1758. He did not live to see the result, but the comet appeared as expected, with some delay caused by the gravity of Jupiter and Saturn. The successful prediction showed that at least some comets were permanent members of the solar system rather than one-time atmospheric events or unexplained visitors. The object was later named in his honour and designated 1P/Halley, with the number 1 marking it as the first recognised periodic comet. The discovery changed comet astronomy. A return could be anticipated, previous records could be organised, future observations could be prepared. The comet was no longer simply something that appeared without explanation. It had an orbit, a history, and a next appointment. Halley's orbit remains highly stretched. Near its closest approach to the Sun, it travels inside the orbit of Venus, At its farthest point, it moves beyond Neptune. Because an object in an elongated orbit moves fastest near the Sun, the comet spends only a small part of its 76-year journey in the region, where it becomes bright and easy to observe. Most of the time it is distant, inactive, and extremely faint. As it moves inward, solar heating begins to release gas and dust from the nucleus. A coma develops, followed by dust and ion tails. Its high speed and retrograde direction mean that encounters with dust released by Halley can also occur at considerable relative speeds. Earth crosses parts of the comet's debris stream twice each year, producing the Eta Aquariid meteor shower in May and the Orionid shower in October. The comet itself is absent from the inner solar system, but old material from its previous visits continues to reach our atmosphere. This is one of the useful features of meteor showers. They allow a comet to produce visible events between its returns. Each pass near the Sun releases particles. Those grains spread along the orbit, and planetary gravity gradually moves the trails into slightly different positions. When Earth crosses one of them, the particles enter the atmosphere and create short streaks of light. No piece of the nucleus needs to reach the ground for the shower to occur. Most particles are very small and are destroyed high in the atmosphere. What appears to be a star falling across the sky may be a grain released from a comet several returns ago. It has spent years moving through interplanetary space before ending its journey in less time than it takes someone to point at it. Halley is not the only member of the group associated with a major meteor shower. Comet 55P/Tempel-Tuttle takes about 33 years to orbit the Sun and is the parent of the Leonids. During ordinary years, the Leonids can be a modest shower. Near some returns of the comet, Earth passes through dense trails of recently released material, and the result can become a meteor storm. The 1966 Leonid storm became famous for producing an extraordinary number of meteors during a short period. Observers described the sky as appearing filled with falling streaks. The effect did not mean the comet was breaking apart directly above Earth. Our planet was simply moving through a particularly concentrated dust trail. Tempel-Tuttle's 33-year period places it near the shorter end of the Halley-type range. Its nucleus is only a few kilometers across, yet the material it has released can create a display visible across a large region of Earth. This difference in scale appears often in comet science. The parent body is small, the debris stream is vast, and the atmospheric result can cover the sky. Comet 109 P/Swift-Tuttle sits much closer to the long end of the group. It takes about 133 years to complete an orbit and has a nucleus estimated to be roughly 26 kilometers wide. Its debris produces the Perseid meteor shower, one of the most widely observed annual showers. Earth crosses the broad stream every August, even though Swift-Tuttle itself last passed through the inner solar system in 1992, and is not expected to return until the 22nd century. The Perseids are usually easier to enjoy than the parent comet. A person can watch them several times during a lifetime without needing to remain available for 133 years. The particles arrive at high speed because the comet's orbit is steeply inclined and its motion differs greatly from Earth's. Many produce bright, fast meteors and lingering trails. Swift-Tuttle has sometimes attracted attention because its orbit comes near Earth's. Detailed calculations show that its known future returns are predictable, and it is not on a current collision course. The broader point is that Halley-type comets can move through the inner solar system at high speed and from directions very different from those of the planets. Careful tracking is therefore important, especially when an object has not been observed for many decades. Another well-known member is Comet 12 P/Pons-Brooks. Its orbit takes about 71 years and carries it from near the orbit of Venus to a distance around Neptune's region. It is known for sudden outbursts in which gas and dust production rises, causing the coma to brighten. Its repeated observations over several returns show how a Halley-type comet can be predictable in orbit while remaining less predictable in behaviour. An outburst may occur when pressure builds below the surface, or when a fracture exposes volatile material. The exact details are often difficult to determine because the nucleus remains hidden inside the bright coma. The result can be a rapid change in appearance. Forecasts may give a general brightness range, only for the comet to brighten unexpectedly and require a hurried revision. Ponsbrook's also demonstrates why returning comets receive numbered periodic designations. The number 12P means it was the 12th comet recognised as periodic. The names Pons and Brooks refer to observers connected with its discoveries and recoveries. In earlier centuries, a comet could be discovered, disappear, and then be found again by someone who did not initially realise it was the same body. Once the orbit was calculated, the records could be connected. Halley-type comets have usually experienced fewer close passages to the Sun than the most frequent Jupiter family comets over the same span of time. A body returning every 75 years receives far fewer intense heating cycles than one returning every 6 years. This can allow it to preserve accessible volatile material for longer, although the real condition depends on its age in the orbit, closest solar distance, composition, and surface structure. A Halley-type comet can still become heavily processed. Halley itself has probably made many returns on a broadly similar orbit. Each one has removed material. Giotto's images showed that most of the visible surface was dark and apparently inactive, while jets emerged from a limited number of sunlit regions. The nucleus was not evaporating evenly. Activity was concentrated where gas found a route through or around the surface layer. Before the spacecraft era, the nucleus could not be seen clearly when the comet was active. It was buried inside the glowing coma. Astronomers estimated its properties indirectly, but the actual surface remained concealed. The 1986 return changed that because several nations sent spacecraft toward Halley in an international observing effort sometimes called the Halley Armada. Japan sent the Suisei and Sakigake probes. The Soviet Union sent Vega 1 and Vega 2, which first visited Venus and then continued toward the comet. NASA's International Cometary Explorer contributed solar wind measurements. Issei's Giotto made the closest and most influential encounter, approaching within roughly 600 kilometers of Halley's nucleus. Giotto had to pass through the dusty coma, while the spacecraft and comet approached each other at a combined speed of about 245,000 kilometers per hour. At that speed, even a tiny grain could cause serious damage. The spacecraft used a protective shield, but dust impacts still affected it. A collision temporarily disturbed its orientation, and the camera stopped working near closest approach. Even so, Giotto survived and returned the first close images of a comet nucleus. The images showed a dark, irregular, elongated body. Halley's nucleus measured roughly 15 kilometers by 8 kilometers, with a surface reflecting only a few % of the sunlight falling on it. Bright jets emerged from active regions, but much of the surface appeared quiet. The brilliant comet seen from a distance was being produced by a nucleus darker than many people had expected. This finding helped replace the image of a clean frozen object with a more realistic picture. The surface contained dark dust and carbon-rich material. Ice was present, but much of it was hidden beneath or mixed with darker substances. Solar heating drove gas through active regions, carrying dust outward to create the coma and tail. Giotto also detected evidence of organic material. In this context, organic means carbon-containing chemistry. It does not mean that the comet was alive or that it had developed a preference for natural food shops. The result mattered because comets preserve material connected with the early solar system, and their carbon-rich compounds may help scientists understand how complex chemistry was distributed among forming planets and smaller bodies. The 1986 return was scientifically valuable, but visually disappointing for many observers on Earth. The geometry placed Halley in an unfavourable position relative to our planet during its brightest period. People who had waited years for a grand display sometimes saw little more than a faint object. The comet had not become weaker merely to be difficult. Earth was simply observing it from an inconvenient location. Its next close passage through the inner solar system will occur in 2061, with viewing conditions expected to be more favourable. The precise brightness cannot be guaranteed decades in advance, but the orbit can be predicted. Some people alive today saw Halley in 1986 and may see it again. Others were born after the last appearance and may have their first opportunity in 2061. The interval gives the comet an unusual place in personal history, because it can mark stages of a human life. The number of returns a person sees is not what makes the group scientifically important. Halley-type comets connect the short-period and long-period populations. They return often enough to establish their identities and calculate their paths, yet their steeply inclined, elongated orbits retain signs of a more distant origin. They show how an object from the Oort Cloud can be moved into a period measured in decades rather than thousands of years. The conversion is not easy. A comet entering from the distant cloud usually moves on a very large orbit. To become Halley-type, it must lose orbital energy through encounters with planets. Jupiter plays a major role, but one encounter rarely produces the finished result. The object may pass through a long sequence of temporary orbits. Some simulations show comets being passed among the giant planets before reaching a more compact path. Many do not survive this process. A comet may be thrown outward again. It may be ejected completely. It can pass too close to a planet or the sun, fragment, or lose enough volatile material to become inactive. The Halley-type objects observed today are the small surviving portion of a much larger flow of bodies whose paths evolve differently. Their high inclinations also make spacecraft encounters difficult. A target moving near the planetary plane can often be reached using a route that takes advantage of planetary motion. A retrograde comet approaches at a much higher relative speed. Matching its orbit would require an enormous change in velocity, so missions such as Giotto perform fast flybys rather than settling alongside the nucleus. A flyby provides only a brief observing window. Instruments must collect data quickly, while the target grows from a faint point into a large object and then recedes again. Dust protection becomes essential. Navigation must be precise because the nucleus is small, dark, and hidden inside a changing coma. The spacecraft may spend years travelling toward an encounter that lasts only hours. Future missions could observe Halley-type comets with more advanced cameras, spectrometers, dust analyzers, and autonomous navigation. Reaching one early, before strong activity begins, would allow the nucleus to be examined before the coma becomes dense. Following it for a longer part of the orbit would be even more valuable, though matching the motion of a steeply inclined or retrograde object remains a major engineering problem. Ground-based astronomy fills many gaps. Large telescopes can detect returning comets while they are still distant. Infrared observations measure dust and thermal properties. Spectroscopy identifies gases. Radar may be possible during favourable approaches. Networks of amateur observers also contribute positions and brightness measurements, providing wide coverage when professional observatories face limited time. Historical observations remain useful as well. A description made hundreds of years ago can help refine an orbit, or reveal whether a comet was unusually bright during a previous return. Ancient observers could not measure the nucleus with spacecraft, but they recorded dates, positions, tail lengths, and changes in appearance. Those records extend the scientific baseline far beyond the age of modern instruments. Every return adds another layer. An orbit becomes more precise. The timing of activity can be compared. Changes in rotation may be measured. Dust trails can be linked with meteor activity on Earth. For Halley-type comets, this process unfolds slowly because the next opportunity may be decades away. The group is familiar in name but not in frequency. Halley, Swift-Tuttle, Temple-Tuttle, and Ponce-Brooks are returning objects, yet most of their journeys take place beyond ordinary observation. Their bright appearances are brief intervals in long orbits spent in cold darkness. Even these extended paths are small compared with the routes followed by another population. A long-period comet takes more than 2 centuries to complete one orbit around the Sun, and some require thousands, hundreds of thousands, or even millions of years. A few have estimated periods extending to roughly 30 million years. From a human point of view, these are not returning visitors in any practical sense. We may calculate that they remain bound to the Sun, but no observer can wait around to confirm the next appearance. Most long-period comets are thought to come from the Oort Cloud, a distant population of icy bodies surrounding the solar system. The cloud has never been photographed directly. Its objects are too small, too dark, and too far away for current telescopes to see as a population. Astronomers infer that it exists because long-period comets arrive from many different directions and follow orbits that extend far beyond the planets. The word cloud is important. The Kuiper belt is arranged mainly in a broad disk beyond Neptune, close to the plane occupied by the planets. The Oort Cloud is thought to form a much more spherical distribution. Its members can orbit above the planetary plane, below it, or at almost any angle. This arrangement explains why long-period comets can enter the inner solar system from unexpected parts of the sky, sometimes moving in the same direction as the planets, and sometimes moving in the opposite direction. The cloud is also extremely large. Estimates vary because there is no visible outer boundary that can be measured directly. NASA places its inner edge somewhere around 2,000 to 5,000 astronomical units from the Sun, with the outer region possibly reaching between 10,000 and 100,000 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun. Pluto, for comparison, travels at roughly 30 to 50 astronomical units. Even the inner Oort Cloud is therefore far beyond the familiar planetary system. At the current speed of Voyager 1, reaching the inner part of the cloud would take centuries. Passing through the entire structure could require tens of thousands of years. The Sun's gravity still influences objects at those distances, but its hold is weak. The gravity of the Milky Way and the effects of passing stars become significant enough to alter their paths. The Oort Cloud sits in a region where the solar system gradually gives way to the wider gravitational environment of the galaxy. The icy bodies did not necessarily form where they are now. The leading explanation begins much closer to the young Sun, among the region where the giant planets were forming. Billions of smaller objects remained after the planets developed. Repeated encounters with Jupiter, Saturn, Uranus, and Neptune scattered many of those objects. Some were thrown out of the solar system completely. Others were placed on distant but still bound orbits. Reaching the Oort Cloud was not simply a matter of being thrown outward once. An object scattered by a giant planet could enter a very elongated orbit, travel thousands of astronomical units from the Sun, and then return to encounter the planets again. Further interactions could remove it, redirect it, or make the orbit even larger. Galactic tides and passing stars could gradually change the orientation and shape of the most distant paths. Over time, a broadly spherical population could develop. The process was probably inefficient. Large numbers of objects were lost to interstellar space, while only a portion remained weakly attached to the Sun. Those survivors became a distant reserve of material left from the early solar system. Estimates suggest that the cloud may contain hundreds of billions or even trillions of icy bodies, although the number remains uncertain because astronomers can study only the small fraction that travels inward. An object stored there can spend billions of years receiving very little heat from the Sun. At such distances, the Sun would appear as a bright star rather than the large disk seen from Earth. The body would remain dark and inactive, following an orbit so large that one circuit could cover a substantial part of the solar system's history. Something must change before that object becomes a visible long-period comet. A passing star may provide a small gravitational pull. The tidal field of the Milky Way may slowly alter the orbit. Interactions within the broader outer solar system may also contribute. The disturbance does not need to push the object directly toward Earth. It only needs to lower the closest point of the orbit enough for the body to begin falling toward the planetary region. The phrase falling toward the Sun is accurate even though the comet is moving along an orbit. Far away, it travels slowly. As the Sun's gravity pulls it inward, its speed increases. It may spend millions of years in the outer part of the journey and then move through the inner solar system in a matter of months. The portion visible to telescopes is only a very small part of the complete orbit. This creates a problem for discovery. A long-period comet can remain too faint to detect until it is already approaching the Sun. Older sky surveys might find one only a few months before perihelion, the point of closest approach. Modern surveys can discover some of them years earlier, especially if the nucleus is large or activity begins at a considerable distance. Even so, astronomers rarely receive the long preparation period available for a known short-period comet. The uncertainty is not limited to the date of discovery. A newly found comet is observed across a short section of an enormous orbit. Early calculations may change as more positions are measured. Astronomers refine the path by following the object over weeks, months, and sometimes years. They also account for the weak forces caused by outgassing, which can slightly push the nucleus away from a purely gravitational trajectory. Many long-period comet orbits are extremely elongated and close to the boundary between a closed ellipse and an open path. A very small difference in the calculated speed can imply a return after a vast interval or no return at all. Planetary encounters can also change the outcome. A comet may arrive on a bound orbit from the Oort Cloud and leave the inner solar system on a path that eventually carries it into interstellar space. This is why astronomers often examine the comet's orbit before and after it passes through the planetary region. The path measured near the Sun has already been affected by the planets. To investigate where the comet came from, researchers calculate backward to estimate its earlier motion. To ask whether it will return, they calculate forward after the strongest encounters have occurred. A long period designation does not automatically mean that the object is making its first visit. Some have approached the Sun before and are returning after thousands of years. Others may be dynamically new, meaning they have never entered the inner solar system or have done so very rarely. The distinction matters because repeated heating changes a comet. A dynamically new comet may have volatile material available close to its surface. It has not experienced hundreds of warm passages like a Jupiter family comet. Activity can begin at large distances as carbon monoxide, carbon dioxide, or other volatile substances turn into gas. The surface may also be fragile because it has not previously been exposed to strong heating and rapid temperature changes. Fresh does not necessarily mean untouched in every sense. Radiation, small impacts, and extreme cold have affected the object during its long storage. Its surface may have developed altered layers. It may also contain material assembled from different regions of the young solar system. Calling it pristine usually means that it has experienced relatively little processing from close solar approaches, not that nothing has happened to it since its formation. The first strong heating can produce complicated behaviour. Gas may escape through newly opened fractures. Dust can lift from the surface. Activity may increase quickly. Sections of the nucleus may break apart if thermal stress, internal pressure, rotation, and weak structure combine in an unfortunate way. Some new comets become bright and impressive. Others disintegrate before observers can decide whether the original predictions were optimistic. This helps explain the poor reliability of early brightness forecasts. A large active comet may brighten steadily and become visible without a telescope. A smaller one may release a great deal of dust for a time and then fade. Another may seem promising while far away, only to weaken when its accessible, volatile supply changes. The orbit can be calculated much more confidently than the physical response of the nucleus. Long-period comets can be larger on average than members of the Jupiter family. A study using data from NASA's WISE spacecraft concluded that long-period comets at least 1 kilometre across were more numerous than earlier estimates suggested, and that their nuclei were, on average, up to twice as large as those of Jupiter family comets. The difference may partly reflect their histories. frequent returners lose material repeatedly, while distant comets can spend most of their existence in cold storage. Observation creates several biases. A larger comet can be detected from farther away. A highly active comet is easier to find than a quiet one of the same size. An object that approaches close to the Sun or Earth receives more attention than one that remains distant. Astronomers therefore do not see a perfectly representative sample of the Oort Cloud. They see the members whose orbits and activity make them observable. Comet Hale-Bopp provides a well-known example of a large long-period comet. Alan Hale and Thomas Bopp discovered it independently in July 1995, when it was more than 7 astronomical units from the Sun. Finding an active comet at that distance was unusual, and gave astronomers a long period in which to prepare for its closer approach. Its nucleus is estimated to be about 60 kilometers across, much larger than that of most familiar comets. The object became visible to the unaided eye for roughly 18 months during 1996 and 1997. Its size, activity, and favourable circumstances produced a display remembered by people who may not otherwise have spent much time observing comets. Hale-Bopp takes about 2,534 years to orbit the Sun under current estimates. That makes it a returning comet, but its schedule is not socially convenient. Its previous visit occurred long before modern astronomy, and its next one belongs to a distant future. During the 1997 appearance, however, telescopes across the world could study gases, dust, jets, rotation, and changes in the coma over an extended period. The comet released several substances while still far from the Sun. Observations of distant activity help scientists determine which volatile materials can drive outgassing at low temperatures. Water ice dominates activity close to the Sun, but cannot explain every distant coma. Carbon monoxide and carbon dioxide can become important before water sublimation grows strong. Comet C/2020 SF3 NEOWISE offered a more recent example. NASA's NEOWISE spacecraft discovered it in infrared images in March 2020. The comet survived its close approach to the Sun and became visible from the northern hemisphere during July. Its nucleus was estimated to be no more than about 4.8 kilometers across, while the visible coma extended far beyond the unresolved central body. Its orbit will not bring it back to the inner solar system for nearly 7,000 years. That interval is short compared with some Oort Cloud comets, but still long enough to remove it from any ordinary idea of a repeat performance. The people who observed it in 2020 were seeing the only appearance available to many generations on either side of them. The comet's popularity also showed how modern technology has changed public observation. Photographers use digital cameras and phones. Spacecraft watched from above Earth's atmosphere. Images travelled around the world within minutes. Earlier societies might have recorded a similar object in a manuscript or drawing. The comet behaved according to the same physics, but the audience had acquired faster methods of sharing the view. Comet C/2013. A1 Siding Spring followed a much larger path. It passed extremely close to Mars in October 2014, giving spacecraft already operating around and on the planet an unusual opportunity to observe a long-period comet. NASA identifies it as an Oort Cloud comet that will not return for roughly 740,000 years. The close passage posed a concern for Mars orbiters because dust released by the comet could strike spacecraft at high relative speed. Mission teams adjusted operations and used the planet as partial protection during the period of greatest risk. The spacecraft then studied the comet and the effects of its material on the Martian environment. No mission had been launched specifically to meet Siding Spring. The comet happened to pass a planet already surrounded by functioning observers, which was an unusually helpful arrangement. A more extreme example of size is C/2014 UN-271, known as Bernardinelli-Bernstein. It was found in archival images from the Dark Energy Survey and had been detected while still near the distance of Neptune. Hubble observations combined with radio data produced an estimated nucleus diameter of about 130 kilometers, making it the largest comet nucleus measured when the result was announced. The object has been travelling inward for well over 1 million years on an orbit lasting about 3 million years. It will not enter the region of the inner planets. Its closest solar approach in 2031 will remain beyond Saturn's orbit at roughly 11 astronomical units. That distance makes it completely harmless to Earth, but its activity is scientifically valuable because it shows that a very large comet can release material while still far from the Sun. At those distances, water ice remains far too cold to drive ordinary near-Sun activity. More volatile substances, particularly carbon monoxide, can escape and carry dust away. Studying that process allows researchers to examine a comet before intense heating has greatly altered the surface. Bernard and Nellie Bernstein also demonstrates that a long-period comet does not need to become a bright naked-eye object to be important. Its path never brings it close enough to produce a display like Hale-Bopp. Powerful observatories are needed to separate the nucleus from its surrounding coma. The scientific value comes from its size, distant activity, and likely connection to the outer Oort Cloud, rather than from its usefulness in holiday photographs. Some long-period comets produce meteor showers even though the nucleus does not return during a human lifetime. Comet C/1911. N1 Kiza has an estimated period of about 2,000 years and is linked with the Aurigid meteors. Earth can encounter old dust trails left during an earlier passage long after the comet itself has returned to the outer solar system. Because the dust has had centuries to spread, predicting these encounters can be difficult. Gravitational effects from planets alter the particles. Radiation pressure affects smaller grains. A dense trail may cross Earth only rarely, producing a strong display during one year and little activity during most others. The meteor shower becomes a delayed record of a comet that is no longer nearby. Long-period comets are also relevant to planetary defense. Their approach speeds can be high, and their first detection may come later than that of asteroids already moving repeatedly through the inner solar system. Their arrival directions are less concentrated around the planetary plane. These features make early discovery valuable, though actual impacts from large long-period comets are rare. Survey telescopes repeatedly scan the sky, comparing images to find points that have moved. Automated systems calculate preliminary orbits and alert observers. Follow-up measurements improve the prediction. Infrared instruments are useful because they can detect thermal emission from dust and help estimate nucleus sizes that visible observations may confuse with reflected light from the coma. Future surveys should find more distant comets earlier. That will improve population estimates and give scientists more time to study activity before the objects approach the Sun. It also creates the possibility of sending a spacecraft to a comet that has never been heated strongly. ESA's Comet interceptor is being developed around that idea. The mission is planned for launch in late 2028 or early 2029 and will wait near the Sun-Earth L2 region until a suitable target is identified. Rather than selecting a known short-period comet years in advance, the spacecraft will remain ready for a newly discovered, dynamically new long-period comet, or possibly an interstellar object. The mission includes a main spacecraft and 2 smaller probes. Before the flyby, they will separate and observe the target from different positions, allowing scientists to build a more complete picture of the nucleus, coma, dust, gas, and surrounding plasma. Earlier spacecraft visited comets that had already passed near the Sun many times. Comet Interceptor is intended to examine one that has experienced far less solar processing. Waiting for an undiscovered target is unusual. Engineers normally prefer to know exactly where a spacecraft is going before launch. In this case, the uncertainty is part of the design. A pristine long-period comet may not be found early enough to build a mission after discovery, so the mission must be built first and the destination selected later. It is the spaceflight equivalent of arriving at a railway station with scientific instruments and deciding which train to board when the timetable updates. Long-period comets provide the most direct observational evidence for the Oort Cloud, because we cannot yet see the cloud itself. Each one carries information about that remote population. Its orbit indicates how objects are distributed. Its composition provides clues about where it formed. Its size contributes to estimates of how much material the cloud contains. Its activity shows what happens when ancient ice encounters stronger sunlight, sometimes for the first time. They also reveal the boundary of the sun's control. An Oort Cloud object remains part of the solar system, but only weakly. A small gravitational disturbance can send it inward. Another can send it away permanently. After the comet passes the Sun and planets, its new orbit may be larger, smaller, or no longer closed. That last possibility brings us to an important distinction. A comet leaving the solar system on an open path is not necessarily an interstellar visitor. The difference can be subtle when an orbit lies close to the boundary. A comet may appear to be leaving the solar system forever, but that alone does not prove it was born somewhere else. Some comets form around the Sun, spend most of their lives in the Oort Cloud, and then receive enough energy from a planetary encounter to escape. Others arrive already moving too quickly for the Sun to capture them. Both can follow open paths, but only the second group is truly interstellar. To separate them, astronomers begin with the shape of the orbit. Most planets, asteroids, and returning comets travel around the Sun on ellipses. An ellipse is a closed path, so the object returns after completing a circuit. A perfectly parabolic path sits at the dividing line between being bound and escaping. A hyperbolic orbit is open. An object following one approaches the Sun, curves around it, and continues outward without completing an orbit. It does not return unless something else changes its course later. The shape is described using a number called eccentricity. A circular orbit has an eccentricity of 0. An elliptical orbit has a value greater than 0 but less than 1. A parabola has a value of exactly 1, while a hyperbola has a value greater than 1. In real observations, the measurements come with uncertainty, and a comet whose calculated value sits only slightly above 1 may require more data before astronomers can decide what the number actually means. That uncertainty matters because the planets can alter the orbit. A comet arriving from the Oort Cloud may originally be moving on an extremely long but closed path. During its passage through the planetary system, Jupiter or another planet can give it a gravitational push. When the comet leaves, its orbit may be hyperbolic even though it formed around the Sun. Calling every such object interstellar would be like calling someone a foreign visitor, because they were seen leaving through an airport. The important question is where the journey began, not simply where it is going. Astronomers therefore calculate more than the orbit observed near the Sun. They estimate the object's path before it encountered the planets. This is often called its original orbit. They can also calculate the future orbit after the comet has passed through the strongest gravitational disturbances. The Sun and planets are usually treated relative to the centre of mass of the solar system, which provides a clearer picture of whether the object was bound before it arrived. Outgassing adds another difficulty. Gas escaping from an active comet acts like a collection of small thrusters. The force is weak, but it can slightly change the comet's motion. If the nucleus is producing uneven jets, the resulting acceleration may make an orbit look a little more open or closed than it would under gravity alone. Researchers must include these non-gravitational effects when the observations are precise enough to detect them. A solar system comet can therefore become hyperbolic in 2 main ways. It may pass close enough to a planet to gain escape speed, or its measured path may appear slightly hyperbolic because of incomplete data and outgassing. Neither situation proves an extrasolar origin. A confirmed interstellar object has a clearly hyperbolic incoming orbit that remains unbound even after planetary influences and measurement uncertainties are taken into account. The speed far from the Sun provides another clue. An Oort Cloud comet can fall inward from an enormous distance, and reach a high speed near the Sun, but much of that speed comes from solar gravity. If the motion is calculated backward, the comet slows as it moves outward and remains weakly bound. An interstellar object still has substantial speed after the Sun's gravitational contribution is removed. Astronomers call this excess hyperbolic speed, or the velocity at infinity. Infinity is being used mathematically here. No one has placed a speed camera at the edge of the universe. Finding a clearly positive incoming excess speed shows that the Sun did not provide all of the object's motion. It was already travelling through interstellar space before entering the solar system. The Sun bends the path and increases the speed during the approach, but it cannot hold the visitor. After perihelion, the object loses the extra speed it gained while falling inward and continues into the galaxy with the motion it had before, modified slightly by the encounter. As of July 2026, astronomers have confirmed 3 interstellar objects passing through the solar system. The first was 1I/Oumuamua, discovered in 2017. The second was 2I/Borisov, discovered in 2019. The third was the active comet 3I/Atlas, discovered in 2025. The letter I in their formal designations marks them as interstellar, while the number records the order in which they were confirmed. 3 objects are not enough to describe the complete population. They are simply the ones that surveys have detected, followed, and confirmed. Interstellar space almost certainly contains many more small bodies ejected from planetary systems, but most are too faint, too small, too distant, or moving through parts of the sky that were not being observed at the right moment. The known sample is strongly influenced by the telescopes available and by the amount of warning each object provides. The first discovery showed how easily one of these visitors can nearly escape attention. The Pan-STARRS Survey Telescope in Hawaii detected Oumuamua in October 2017, after the object had already passed its closest point to the Sun and was moving outward. Astronomers had only a limited period in which to observe it before it became too faint for even powerful telescopes. Its name comes from Hawaiian and is commonly explained as referring to a messenger or scout arriving first from a distant place. Its formal designation, 1I/2017 U1, marked the creation of a new interstellar category. Before this object appeared, astronomers expected that material ejected from other planetary systems should occasionally pass near the Sun. The prediction was reasonable. The actual object was less cooperative. Oumuamua came within about 1/4 of an astronomical unit of the Sun, and moved on a strongly unbound path. Its high incoming speed and trajectory showed that it could not have started as an ordinary solar system object. When calculations traced the motion backward, it arrived from interstellar space without having received the required speed from a close encounter with one of our planets. At first, astronomers classified it as a comet because comets commonly occupy highly elongated or open-looking paths. Telescope images, however, showed no visible coma or tail. It appeared as a point of light, so it was then treated more like an asteroid. The situation changed again when precise tracking revealed a small acceleration that could not be explained by gravity alone. Outgassing offered a natural explanation, although no obvious cloud of gas or dust had been seen. This placed Oumuamua near the boundary between an asteroid and a comet. It may have released gas with very little dust, creating activity too faint or too unusual for the available observations to detect directly. Several volatile substances have been proposed, and other physical explanations have also been studied. The object disappeared before astronomers could collect the measurements needed to settle the question. Its changing brightness showed that it was rotating or tumbling, and that its shape was far from spherical. Early interpretations often described it as extremely long and narrow, although later models also considered a flattened shape. Because no telescope resolved the surface, every illustration remains an informed reconstruction, rather than a photograph. NASA's summary describes the object as highly elongated, reddish, and tumbling through space. The lack of a direct image created a large amount of public speculation. Unusual does not mean artificial, and an unexplained detail does not require machinery. Scientists test natural models by comparing them with the measured brightness, motion, temperature, and lack of visible dust. The available evidence established that Oumuamua was interstellar. It did not establish exactly what its surface looked like or which material produced the small acceleration. Its late discovery prevented a spacecraft encounter. By the time astronomers understood what they were observing, the object was already leaving at high speed. A mission designed after discovery would have needed to catch something with a substantial head start, moving on a steep and unbound path. Spacecraft are capable of impressive journeys, but they still prefer a destination that has not already left. The second known visitor was much easier to recognize as a comet. Gennady Borisov, an amateur astronomer and telescope maker, discovered it on August 30th, 2019. Additional observations quickly showed that its orbit was strongly hyperbolic. Unlike Oumuamua, it developed a clear coma and released enough gas and dust for astronomers to study its chemistry. It received the designation 2I/Borisov and became the first confirmed interstellar comet. Borisov looked reassuringly familiar. It had a compact nucleus hidden inside a dusty coma, and its activity increased as it approached the Sun. Water production rose in a pattern similar to that of many solar system comets. Several detected molecules also appeared in familiar proportions. A comet formed around another star was following processes that astronomers already understood from objects formed around our own. The similarities were scientifically important. Planet-forming disks around other stars differ in size, temperature, chemistry, and history, but the basic process of building icy bodies may operate widely. Dust grains combine, volatile compounds freeze, larger objects form. Planets then scatter some of those bodies into distant reservoirs or out of their systems entirely. Borisov also contained a major chemical surprise. Radio observations found an unusually high concentration of carbon monoxide compared with water. The measured carbon monoxide abundance was far above the average for comets observed at similar distances from the Sun. This suggested that Borisov may have formed in a very cold part of its original planetary system, where carbon monoxide could remain frozen efficiently. A cold formation region could exist far from a Sun-like star or closer to a smaller, dimmer red dwarf. Another possibility is that Borisov was a fragment of a larger body, with carbon monoxide-rich material near its surface. The observations could not identify the original star, but they showed that the comet's chemistry did not fit neatly inside the range familiar from our solar system. The nucleus was relatively small, with estimates close to 1 kilometer across. NASA's swift observations indicated that a large fraction of its surface was active near its closest solar approach. At peak activity, it released roughly 30 litres of water per second. That sounds substantial in a kitchen and modest beside an ocean, which is often how comet measurements behave. Hubble followed the object as it moved through the solar system at roughly 177,000 kilometers per hour. Images showed dust concentrated around the unseen nucleus. Borisov passed its perihelion in December 2019 and continued outward, remaining permanently unbound to the Sun. Observations also suggested that the nucleus changed as it left the Sun. Small pieces may have separated, and activity declined as the comet cooled. This was not unusual comet behavior. The unusual part was that the material had formed around another star, spent an unknown length of time travelling through interstellar space, and happened to pass close enough for our telescopes to examine it. Where Borisov came from remains unknown. Tracing an interstellar object back to a particular star is much harder than following its path through the solar system. Stars are moving. The comet may have travelled for millions or billions of years. Small changes in the estimated motion become enormous positional uncertainties when calculated backward across such long intervals. Encounters with other stars and the galaxy's gravitational field add further complications. It was probably ejected by gravitational interactions in its home system. A giant planet can scatter a small icy body outward, just as Jupiter and the other giant planets scattered comets during the early history of our solar system. Some remain in distant clouds, others gain enough energy to escape. Once released, they orbit the centre of the Milky Way rather than the star that formed them. Young planetary systems may be especially efficient at producing such objects. Planets migrate, exchange energy, and disturb large populations of leftover material. Binary stars can also destabilize small bodies. The result is a galaxy containing objects that began in planetary disks but no longer belong to their original systems. Most of those travellers will never pass close to another star. Interstellar space is too large, and stars occupy a very small portion of it. A comet can wander for an immense period without receiving enough heat to become active. Its surface is exposed to cosmic radiation and impacts from interstellar dust, but its deeper material may remain cold. When one enters a new planetary system, it encounters a star from a direction and speed determined by its galactic motion. It may pass far outside the planets and remain undiscovered. A smaller number cross the region covered by survey telescopes. Fewer still become bright enough and remain visible long enough for an orbit to be confirmed. That is why the discovery of the third known object, 3I/Atlas, was so valuable. It was first reported on July 1, 2025, by the NASA-funded Atlas Survey Telescope at Rio Hurtado in Chile. Archival searches later found earlier observations, including images from June 2025 and detections in test data from May. Those pre-discovery measurements extended the observed path and improved the orbit. The orbit clearly showed an origin outside the solar system. 3I/Atlas followed a hyperbolic path and would not remain bound to the Sun. It was also visibly active, with an icy nucleus surrounded by a coma of gas and dust. Unlike Oumuamua, there was no serious difficulty deciding whether this object belonged in the comet category. The comet reached perihelion around October 30th, 2025, at approximately 1.4 astronomical units from the Sun, just inside the orbit of Mars. Its closest approach to Earth remained about 1.8 astronomical units away, or roughly 270 million kilometers. It posed no impact threat. More than 4,000 observations submitted to the Minor Planet Center confirmed the safe trajectory. The geometry allowed spacecraft already spread across the solar system to observe it from several locations. Hubble, Webb, TESS, Swift, Spherex, Mars Orbiters, the Perseverance rover, Parker Solar Probe, and several travelling spacecraft collected information. No mission had been built specifically for 3I/Atlas, but the number of instruments available turned its passage into a broad observing campaign. Hubble images showed a cocoon of dust surrounding the nucleus. Separating the solid body from the bright coma was difficult, so the size could not be given as one exact number. Observations placed the diameter somewhere between about 440 metres and 5.6 kilometres. Even the upper estimate is small compared with the coma visible around it. After passing too close to the Sun's direction in the sky for easy observation, 3I/Atlas reappeared in December 2025. TESS observed it again in January 2026, while other missions followed its changing activity as it moved outward. The comet is now leaving and will never return to the solar system. Its measurements will remain available long after the object itself becomes unreachable. Webb observations produced the most detailed chemical information yet obtained from an interstellar comet. Measurements released in June 2026 found isotope ratios involving heavy hydrogen and carbon that differed substantially from those measured in solar system comets. Researchers interpreted the early results as evidence that 3I/Atlas formed in an environment unlike our own, and may have been ejected from its original system billions of years ago. Webb also detected methane during later observations, while other instruments measured water, carbon dioxide, carbon monoxide, dust, and organic molecules in the coma. Each substance responds differently to temperature, so the changing mixture helps researchers investigate the layers and formation conditions of the nucleus. The differences between Borisov and 3I/Atlas are already instructive. Borisov showed a very high carbon monoxide abundance, but also resembled solar system comets in several other ways. The isotope ratios measured in 3I/Atlas appear more unusual. 2 interstellar comets do not define the full range, but they already show that material ejected from other planetary systems is not chemically identical. Oumuamua adds another form to the sample. It showed no visible coma, but experienced a small non-gravitational acceleration. Borisov appeared as a fairly recognizable active comet with unusual carbon monoxide. 3I/Atlas was clearly cometary, and could be observed by a large network of modern instruments. The first 3 visitors therefore differed enough to prevent astronomers from treating interstellar objects as one simple class. This variety is not surprising. Our own solar system contains Jupiter family comets, Halley-type comets, Oort Cloud comets, centaurs, dormant nuclei, active asteroids, and objects with unusual compositions. Other planetary systems have different stars, planet arrangements, temperature profiles, and histories. The material they eject should also vary. The difficult part is building a sample large enough to compare. 3 confirmed interstellar objects provide valuable case studies, but they do not support firm statements about what is typical across the galaxy. Discovering more will require wide surveys that repeatedly image large sections of sky and identify faint-moving objects quickly. Earlier detection is particularly important. Oumuamua was found after perihelion, leaving little observing time. Borisov was discovered before perihelion, allowing months of preparation. 3I/Atlas was detected far enough out for a coordinated campaign, and had appeared unnoticed in earlier survey data. Every additional week can allow more observatories to schedule measurements. A spacecraft encounter remains difficult but possible under favourable circumstances. The target must be discovered early enough, and its path must pass within reach of a waiting mission. Interstellar objects move rapidly and may approach from far outside the planetary plane. A spacecraft designed for one direction cannot instantly turn toward another, especially when a large change in speed is required. A prepared interceptor offers a better chance than designing a mission after discovery. It could wait in space with fuel available, receive the target orbit, and begin travelling before the object reaches perihelion. Even then, the encounter would probably be a fast flyby rather than a slow escort. Instruments would have limited time to image the nucleus and sample the surrounding dust and gas. The reward would be considerable. Telescopes study sunlight reflected or emitted by distant material. A spacecraft could photograph the surface directly, measure dust grains one by one, analyze gases at close range, and observe how activity changes across the nucleus. It would examine material formed around another star without needing to travel to that star. Interstellar comets provide a form of natural sample delivery, although the sample does not stop. The object enters the solar system, becomes active, passes the sun, and leaves. We cannot select the source system, arrival direction, or convenient date. We can only improve the chance of noticing the next one early. The number of discoveries should rise as surveys become more sensitive. A larger telescope can detect smaller or more distant objects. Faster data processing can recognize unusual motion before the object fades. Repeated coverage can reveal an incoming body while it is still beyond the orbit of Jupiter or Saturn, especially if volatile material has already formed a coma. The most useful future discoveries may include objects that behave differently from all 3 known visitors. One may remain completely inactive, another may be rich in a substance rarely seen in solar system comets. A large interstellar comet could become visible without a telescope. A very small one might be detected only because it passes unusually close to Earth. None of these possibilities requires an impact, and most detected paths are likely to remain safely distant. A hyperbolic orbit should therefore be treated as the beginning of an investigation, not the final answer. Astronomers ask whether the incoming path was already unbound. whether a planet could have provided the extra energy, whether gas jets are changing the motion, and how confidently the measurements separate a weakly bound comet from an interstellar one. Once an extrasolar origin is confirmed, the object becomes evidence from another planetary system. Its gases record formation temperatures. Its dust contains minerals assembled around another star. Its rotation and shape may reveal collisions, erosion, or the conditions of its ejection. Even an unresolved point of light can answer questions about how planets form and how often they remove smaller bodies from their systems. These visitors have no return ticket because the sun never captures them. The phrase does not mean they travel in a straight line. Solar gravity bends each path into a hyperbola, increases the speed during the approach, and sends the object outward in a new direction. The encounter can alter its route through the galaxy, but not enough to turn it into a permanent solar system member. After the comet leaves, it resumes a long journey between stars. It may never pass close to another planetary system. If it does, the event may occur millions of years from now, when its surface, rotation, and trajectory have changed further. From that future system, it would arrive as an object with no visible connection to the star around which it originally formed. The 3 visitors already observed show how much can be learned during one passage and how much remains unknown after it ends. The orbit can prove an interstellar origin, but it may not identify the original star. Spectroscopy can reveal gases, but it cannot always show how the materials are arranged inside the nucleus. Brightness changes can suggest a shape, but they do not replace a direct image. Origin is only one way to classify a comet. A hyperbolic visitor may pass at a comfortable distance from the Sun, as 3I/Atlas did, or it may approach much more closely. Once the closest point of a comet's orbit becomes extremely small, its place of origin is no longer the most urgent part of the story. A comet may have come from the Oort Cloud, the scattered disk, or a family created by an earlier breakup. Near the Sun, all of those histories meet the same immediate problem. The nucleus must survive intense radiation, rapid material loss, strong gravitational stress, and a passage through the outer solar atmosphere while moving at several 100,000 kilometers per hour. A sun-grazing comet is one whose orbit carries it exceptionally close to the Sun at perihelion. There is no single definition used in every scientific context, but NASA commonly describes sun-grazers as comets passing within about 1.37 million kilometers of the Sun. Many travel much closer, sometimes passing only tens of thousands of kilometers above the visible solar surface. ESA has also used a practical limit of roughly 0.01 astronomical units, or about 1.46 million kilometers. The 2 descriptions identify the same general population, comets whose perihelia place them in an environment where ordinary comet activity becomes extreme. A sun-skirting comet also passes close to the Sun, but not as close as the most extreme sun-grazers. The difference is useful rather than perfectly official. Sun-skirters receive intense heating and can brighten strongly, but their wider paths give them a better chance of surviving. Members of several groups found in SOHO images, including the Maya, Marsden and Kracht groups, are often described as sun-skirters rather than true Kreutz-type sun-grazers. ESA notes that the Kreutz comets approach roughly 10 times closer to the Sun than objects in several of these other groups. Distance makes an enormous difference because the intensity of sunlight rises rapidly as an object approaches the Sun. At half Earth's distance, a comet receives about 4 times as much solar energy per square meter. At 1/10 of Earth's distance, it receives about 100 times as much. A sun-grazer moving only a few solar radii from the centre of the Sun is exposed to an energy input far beyond anything experienced by an ordinary short-period comet near Earth's orbit. Much of that energy goes into sublimating ice. Water, carbon dioxide, carbon monoxide, and other frozen compounds turn into gas and escape. Close enough to the Sun, water ice is no longer merely producing a few active jets. Large areas of the surface can erode rapidly. The escaping gas carries dust, rock grains, and fragments into space, creating a bright coma and tail while steadily reducing the nucleus that supplies them. NASA describes intense sublimation, radiation pressure, the solar wind, and gravitational stress as the main hazards faced during these encounters. Sublimation also cools the surface. Energy used to convert ice into gas is energy that does not immediately raise the temperature of the remaining material. This can delay complete destruction and helps explain why a sufficiently large nucleus may retain solid material during a brief closed passage. It is not protection in the comfortable sense. The comet is cooling itself by losing the substance from which it is made, rather like preventing a block of ice from becoming hot by allowing most of the block to disappear. The rate of loss depends on the nucleus's size, composition, porosity, rotation, and surface structure. A thick dust layer may insulate ice for part of the approach, then fail when gas pressure builds below it. A rapidly rotating nucleus spreads sunlight across different areas, while a slowly rotating one can leave one side exposed for longer. Fractures provide routes for gas. Weakly joined sections may separate when activity rises. Two comets following almost identical paths can therefore experience very different outcomes. Solar gravity creates another problem through tidal force. The side of the nucleus nearer the Sun feels a slightly stronger gravitational pull than the far side. For a strong compact object, the difference may be manageable. Comet nuclei, however, are often porous and weakly bonded mixtures of ice and dust. If the tidal stress becomes greater than the body's internal strength and self-gravity, the nucleus can stretch, fracture, or separate into pieces. NASA identifies these strong tidal forces as one reason many sun grazers do not survive perihelion. Heating also occurs unevenly and very quickly. A comet falling inward may go from strong activity to severe erosion over a short period. Heat penetrates the surface at a limited rate, so the outer layers expand, crack, and lose material while deeper regions remain colder. Gas can become trapped below a crust. If it finds a sudden route outward, an outburst may remove part of the surface or contribute to fragmentation. The solar corona adds more interactions. This outer atmosphere reaches temperatures of more than 1,000,000 degrees, but it is extremely thin. Temperature and heat are not the same thing. The individual particles in the corona carry high energies, yet there are far fewer of them than in a dense atmosphere. A comet is not entering anything resembling a 1,000,000-degree oven full of air. It is passing through a sparse plasma while also receiving intense radiation from the sun beneath it. Material released by the comet becomes ionized and interacts with the corona's magnetic field. The shape and motion of a plasma tail can trace magnetic structures that would otherwise be difficult to observe. For this reason, sun grazers act as accidental probes of the solar atmosphere. Scientists can use their tails to examine magnetic field directions, electron densities, temperatures, and flows within the corona. This scientific benefit was not the reason most solar observatories were built. The Solar and Heliospheric Observatory, better known as SOHO, was designed to study the Sun, its interior, its atmosphere, and the solar wind. Its ability to discover comets emerged from the design of its coronagraphs. A coronagraph places an artificial disk over the bright solar surface, allowing the much fainter corona around it to become visible. Small comets that would be hidden in daylight and solar glare can appear as moving points or streaks in those images. SOHO was launched in 1995 as a joint ESA and NASA mission. It was not expected to become history's most productive comet detector, but its wide and nearly continuous view of the region around the Sun gave it an advantage no traditional night sky telescope could match. On March 25, 2024, a citizen scientist found the 5,000th comet discovered in SOHO data. NASA reported in 2026 that the total had moved beyond 5,000, and that over half of all known comets had first been identified by contributors to the Sungrazer project. Many of those contributors are amateur observers working from computers at home. Images from SOHO are made available online, and volunteers examine sequences for faint-moving objects. A candidate must appear in the expected positions across several frames and move consistently toward or away from the Sun. The discovery is then checked. Its orbit is estimated when enough data exist, and the object may receive an official comet designation. The process requires patience, because coronagraph images contain stars, planets, cosmic ray marks, instrument effects, and material moving through the solar atmosphere. A genuine comet may be visible for only a few frames before fading or passing behind the instrument's occulting disk. It can resemble a small smudge moving across a complicated background, which is not how discovery is presented in most films, but is closer to how astronomy often works. The overwhelming majority of the classic sungrazers found by SOHO belong to the Kreutz group. NASA and ESA have reported that roughly 85% of SOHO's comet discoveries in earlier surveys followed the Kreutz path. These objects share closely related orbits because they are fragments descended from a much larger parent comet that broke apart, with later fragments splitting again during subsequent passages. The family is named after Heinrich Kreutz, a 19th century astronomer who studied several bright comets and showed that their paths were related. The best explanation is not that many separate comets independently selected almost the same extreme orbit. They are members of a fragmentation family, produced as one large object divided into pieces, and those pieces continue dividing. ESA describes a likely orbital period of roughly 800 years for the major fragments and notes that a comet observed in antiquity may have belonged to the same extended family. A small Kreutz fragment may be only a few meters or tens of meters across. It can remain invisible during most of its orbit and appear only when intense heating releases enough dust for a coronagraph to detect it. Many do not emerge after perihelion. Their final observation is a brightening point moving toward the occulting disk, followed by no corresponding object on the other side. This does not always mean the nucleus strikes the visible surface of the Sun. Most sun-grazing paths pass above the photosphere, through the lower corona. ESA distinguishes a comet that passes extremely close from a hypothetical sun striker that directly hits the Sun, and notes that no comet has been definitively observed reaching the photosphere intact. In most cases, the nucleus is destroyed by heating and stress before an impact could occur. Larger Kreutz members can survive long enough to become major naked-eye comets. Comet Ikeyaseki, discovered in 1965, was one of the brightest comets of the 20th century. It passed within roughly 650,000 kilometers of the solar surface, became visible in daylight, and split into pieces near perihelion. Its bright appearance and related orbit identified it as a major Kreutz family member, rather than one of the tiny fragments later found by SOHO. The Great September Comet of 1882 was another exceptionally bright Kreutz sungrazer. It passed very close to the Sun and broke into several visible components. Before spacecraft and digital cameras, astronomers followed those fragments through telescopes and compared their positions. Such observations helped establish that breakup near perihelion was not a rare accident, but a major part of the family's history. Fragmentation can increase brightness temporarily. When a nucleus splits, fresh material is exposed and the total active surface area grows. More gas and dust can escape, creating a stronger coma even while the solid body is being destroyed. A comet may therefore become brightest at the moment its chances of survival are falling. Visual success and physical health are not the same measurement. Comet C/2011 W3. Lovejoy provided one of the most surprising modern examples. Australian amateur astronomer Terry Lovejoy discovered it from the ground in November 2011. Orbital calculations showed that it was a Kreutz sungrazer heading toward a perihelion only about 120,000 kilometers above the solar surface. Many specialists expected the nucleus to be destroyed. Several spacecraft watched its approach on December 15, 2011. SOHO, Stereo, the Solar Dynamics Observatory, Proba 2 and other instruments followed different parts of the event. Lovejoy disappeared into the bright region near the Sun, passed through the corona, and then reappeared. Its survival surprised researchers because the estimated nucleus was not thought large enough to endure such an extreme passage. Survival did not mean the comet passed without damage. Its pre-perihelion tail did not simply remain attached and curve around the Sun. The material was affected by the corona, solar wind, radiation pressure, and magnetic field. After the nucleus reappeared, a new tail developed as more dust and gas were released. Spacecraft observations followed these features and used them to study conditions close to the Sun. Lovejoy became visible from the southern hemisphere after perihelion, displaying a long tail before fading. The event showed that the survival boundary is not determined by distance alone. Size, structure, mass loss rate, and the exact path all matter. A slightly smaller or weaker object on the same route might have disappeared completely. The comet also demonstrated the difference between surviving perihelion and remaining unchanged. A nucleus can lose a large portion of its mass, fragment internally, or continue breaking down after leaving the closest point. The phrase "survived the Sun" means that some coherent nucleus emerged and continued producing activity. It does not mean that the object left in the condition in which it arrived. Comet C/2012 S1 Ison produced the opposite result 2 years later. It was discovered in 2012 while still far from the Sun, and was followed by a large international observing campaign. Because it was an Oort Cloud comet approaching the inner solar system, and was expected to pass about 1.2 million kilometers above the solar surface. Early forecasts considered the possibility that it might become exceptionally bright. It was a sun grazer, but it did not belong to the Kreutz family. Before perihelion, Ison was already releasing dust and gases at large distances. Carbon dioxide and carbon monoxide helped drive some of its earlier activity before water sublimation became dominant. Spacecraft and ground observatories measured its changing coma while predictions were repeatedly adjusted. Some forecasts described a possible daylight comet. Others emphasized that a small nucleus facing its first intense solar encounter might not remain intact. On November 28, 2013, Ison underwent severe heating near perihelion and was torn apart. Images initially showed material emerging from the region near the Sun, raising the possibility that a small nucleus had survived. The remaining feature then spread and faded. NASA's later assessment is that the comet broke into pieces before or during its closest passage and did not continue as an intact active nucleus. Ison's failure was not a wasted observation. The campaign produced a very large comet dataset from more than a dozen spacecraft and many ground-based facilities. Researchers observed the development and destruction of a dynamically new comet under rapidly changing conditions. Knowing that the nucleus failed is itself useful because it places limits on its strength, size, structure, and response to heating. Predictions were difficult because the nucleus was hidden inside the coma and could not be measured directly with high precision. Brightness does not reveal size cleanly. A small nucleus with a large active fraction can appear brighter than a larger one with a sealed surface. Dust production can make a comet look impressive even when the solid body is becoming unstable. This is why comparisons between Lovejoy and Ison require care. Lovejoy passed much closer to the solar surface, and yet emerged. Ison passed farther away and disintegrated. The difference does not mean the more distant route was somehow hotter. Lovejoy may have had enough size or structural integrity to preserve a central portion during the brief encounter, while Ison may have been smaller, weaker, or already fragmenting before perihelion. Orbit alone cannot provide a complete survival forecast. The duration of exposure matters as well. A comet approaching at high speed spends limited time in the most extreme region. A larger object may lose an enormous outer layer without allowing heat to reach the center before it moves away. A smaller object can be consumed entirely. The nucleus's path, rotation, and ability to cool itself through sublimation all affect the balance. Sun-skirting comets face a less severe version of these processes, Their perihelia lie farther from the solar surface, reducing both radiation and tidal stress. They may still brighten greatly, release large amounts of material, and experience fragmentation, but survival is more common. Some return periodically and can be followed during repeated passages. Comet 96P/Mach-Holz 1 is a useful example of an object moving on an unusual orbit close to the Sun without following the extreme Kreutz path. It has been observed repeatedly by SOHO and is linked through orbital studies with the Marsden and Cracked groups of small sun-skirting comets. It may also be associated with several meteor streams encountered by Earth. These relationships show that fragmentation families are not limited to the Kreutz group. A larger periodic comet can release or split into smaller objects that gradually spread along related paths. Some pieces may remain observable from the ground. Others appear only in coronagraph images when they approach the Sun. Dust released through the same extended process can eventually cross Earth's orbit as meteoroids. The Maya group follows another distinct set of sun-skirting orbits. Its members generally remain farther from the Sun than Kreutz fragments, and often survive their close approaches, although they are too faint to follow once they move away from the coronagraph's field of view. The limited observing arc can make it difficult to determine exact periods or connect individual returns. When several comets appear in similar images over a short time, it may look as though they are travelling together. They can be fragments occupying nearby positions along the same orbit, but apparent closeness on a flat image does not always mean physical closeness in space. The chronograph shows projected positions against the sky. Detailed orbital measurements are needed before a genuine relationship is established. SOHO images also frequently show comets close to coronal mass ejections. This has encouraged claims that an incoming comet caused a solar eruption. The visual timing can be striking, but the events are generally coincidences. The Sun produces coronal mass ejections frequently, while SOHO watches the region almost continuously. In documented examples, eruptions began before the comet reached the relevant area, or occurred in a different location from the comet's path. A small comet does not contain enough energy to reorganize the Sun's large magnetic structures in the manner required to produce a major CME. The comet can still be affected strongly by an existing solar eruption. A coronal mass ejection carries plasma and magnetic fields outward. When this disturbance reaches a comet's ion tail, the tail may bend, develop waves, or disconnect. Solar observatories use these reactions to examine how the magnetic disturbance moves through interplanetary space. Near the Sun, the interaction becomes easier to see, because the comet is moving through stronger magnetic fields and denser coronal plasma. Extreme ultraviolet instruments have detected emissions from material released by sun grazers. Different atoms and ions glow at characteristic wavelengths after interacting with the solar atmosphere, allowing researchers to study both the cometary material and the corona. A small nucleus can briefly place material in regions that are difficult for spacecraft to sample directly. The gas and dust trace flows around magnetic structures. Its destruction marks where sublimation and plasma interactions become overwhelming. In this role, the comet is not a controlled scientific probe. Its mass, composition, and exact structure are poorly known, and it cannot carry calibrated instruments. It remains useful because the Sun performs the experiment while multiple telescopes observe the result. Parker Solar Probe now travels through parts of the corona and makes direct measurements of particles and fields. It has also observed a small sun-grazing comet, SOHO-4063, during a solar pass in September 2020. The images gave scientists another viewing angle on a type of object usually seen mainly by SOHO's coronagraphs. Not every object seen near the Sun is a sun grazer. A bright comet can enter SOHO's wide field, while remaining millions of kilometers from the solar surface. Comet C/2024, G3 Atlas, for example, appeared in SOHO images during January 2025, while passing about 13 million kilometers from the Sun. It was a close and active comet. but its distance was much greater than that of a classic sungrazer. The distinction helps prevent the term from becoming a general label for any comet photographed beside the Sun. A normal comet can look extremely close in a two-dimensional image because the line of sight places it near the solar disk. Orbital calculations reveal the actual separation. For genuine sun grazers, the final outcome usually falls into a few broad patterns. A very small nucleus may disappear before perihelion, leaving a fading dust trail. A somewhat larger object may reach perihelion and fragment, producing several pieces or a diffuse cloud. A strong nucleus may survive as a reduced body and develop a new tail after the passage. Rare large members can remain bright enough for observation from Earth once they move into the dawn or evening sky. None of these outcomes is perfectly predictable. The nucleus is concealed, its internal strength is uncertain, and activity can alter the rotation shortly before perihelion. New fractures may form during the final hours. A comet that appears stable can break suddenly. Another that looks unlikely to survive may emerge with enough material to continue. Repeated SOHO discoveries have turned what once looked like a rare category into a common small body process. Great sun grazers visible from Earth remain uncommon, but tiny fragments pass near the Sun frequently. Most are never seen before entering the coronagraph's field and are never seen again afterward. Their brief appearances reveal the continued breakup of older parent bodies and the gradual removal of cometary material from the solar system. The Sun does not need to absorb a nucleus directly to remove it. Sublimation turns ice into gas. Dust is carried into the tail. Tidal stress separates weak sections. Radiation pressure spreads the fragments. The remaining particles continue on related orbits, fall into the Sun later, or disperse until they're too small and faint to track. This process is one possible end for a comet, but extreme heat is not required for comet-like activity. In fact, some of the most difficult objects to classify are found in a region where the Sun is far weaker and where astronomers once expected almost every small body to remain dry and inactive. They move among ordinary asteroids on comparatively stable, near-circular orbits, yet they release dust and sometimes gas as comets do. After following nuclei through this coronum, the next useful move is outward to the main asteroid belt, where the conditions are much less violent, but the boundary between an asteroid and a comet becomes even harder to define. This region lies between the orbits of Mars and Jupiter, and contains a large population of small bodies that usually appear inactive. They travel around the Sun on stable, asteroid-like paths, reflecting a little sunlight and producing no visible atmosphere. Every so often, however, one develops a cloud or tail of dust and begins to look like a comet. The broad term for such an object is active asteroid. An active asteroid follows an orbit normally associated with asteroids, but loses material strongly enough for astronomers to detect it. The escaping material may form a coma, a narrow tail, several separate tails, or a diffuse trail along the orbit. The appearance can resemble ordinary comet activity, but the cause is not always sublimating ice. Impacts, rapid rotation, structural failure, and thermal damage can all release dust without requiring a traditional cometary nucleus. A main belt comet is a more specific kind of active asteroid. It moves on a main belt orbit, and its activity is thought to be driven mainly by the sublimation of buried or exposed ice. The two terms are therefore related, but they are not interchangeable. All main belt comets are active asteroids, while not all active asteroids are main belt comets. One group is defined partly by the physical cause of its activity. The broader group includes almost any asteroid-like body that has started throwing material into space for reasons of its own. This distinction can be difficult to make from a photograph. A tail tells astronomers that dust has left the surface. It does not immediately explain why. Dust released by sublimating gas can be pushed into a tail by sunlight. Dust blasted out during a collision can be pushed into a tail by the same sunlight. Loose grains sliding from a rapidly rotating body receive the same treatment. From a distance, solar radiation pressure tidies several different events into shapes that look inconveniently similar. The best evidence for sublimation is repeated activity near the same position in the orbit. A collision is normally a one-time event. It can produce a cloud that fades over weeks or months, but it should not repeat each time the object approaches the Sun. If an asteroid-like body becomes active during one perihelion passage, grows quiet as it moves outward, and then becomes active again near a later perihelion, solar heating provides a much more convincing explanation. Recurrent activity was central to establishing the main belt comet category. The first recognised member is 133P/Elst Bizarro. It has both an asteroid number 7968 and a periodic comet designation 133P. That double identity is appropriate because the object occupies the region where the older categories begin to overlap. It follows a stable orbit in the main belt, and is dynamically difficult to distinguish from neighbouring asteroids, yet it has repeatedly produced a narrow dust tail around perihelion. Its activity is weak compared with that of a typical comet approaching the inner solar system. A large glowing coma does not surround it, and its dust production is modest. The active area may occupy only a small portion of the surface. Models and observations are consistent with a localised patch of ice that becomes warm enough to sublimate during a favourable season, perhaps after an impact exposed material that had previously been covered. A dusty mantle over most of the body may reduce gas loss and help preserve ice below the surface. The seasonal part is important. An object's distance from the Sun is not the only factor controlling its temperature. The direction of its spin axis determines which areas receive sunlight during different portions of the orbit. A patch near one hemisphere may become active when that hemisphere experiences its local summer. The object can remain near the same general solar distance, while the active region moves from sunlight into shadow as the body continues around the Sun. This produces activity that can begin before or after the exact point of closest approach. Heat also takes time to move through a surface layer. If the ice lies beneath dust, the strongest sublimation may occur after perihelion, when warmth absorbed earlier has reached the buried material. A delayed response does not mean sunlight is uninvolved. It means the nucleus has insulation, thermal inertia, and no obligation to operate like an electric kettle. The existence of ice in the asteroid belt was once considered surprising, because the region is much warmer than the distant reservoirs that supply traditional comets. Exposed surface ice would not remain stable for billions of years across much of the belt. It would gradually sublimate and disappear. Ice buried beneath insulating dust or rock, however, can survive much longer, particularly in the cooler outer part of the belt. Thermal models and observations support the possibility of ancient subsurface ice preserved inside some asteroids since the early solar system. That ice does not need to cover the entire object. A collision may excavate a small crater and remove the protective layer above one deposit. A fracture may connect a buried pocket to the surface. Once sunlight reaches the newly exposed material, sublimation begins. Escaping gas carries dust away, and an object that looked like an ordinary asteroid during earlier observations develops comet-like activity. The process may be temporary. Exposed ice can be depleted. Dust too large to escape may fall back and rebuild an insulating mantle. The active area can become sealed again after a few orbits. This means many icy asteroids may remain invisible as such. Astronomers discover only those that happen to be active while a telescope is looking, and the active period may occupy a very small part of the object's lifetime. The second foundational example was 238P/Reed. It showed activity more than once, supporting a sublimation-driven explanation. For years, astronomers inferred the presence of ice mainly from the repeated dust release. Directly detecting water gas was difficult because these objects are small, faint, and relatively far from the Sun. Their gas production is much weaker than that of the brighter comets, usually targeted by spectrometers. That situation changed when the James Webb Space Telescope observed two 38P. Webb's near-infrared spectrograph detected water vapour in its coma, providing the first direct spectroscopic confirmation of water gas around a main belt comet. the detection demonstrated that water ice can survive in the main asteroid belt and can still drive present-day activity when warmed by the sun. The result also introduced a chemical puzzle. Webb did not detect a significant carbon dioxide coma around 238p. Carbon dioxide is commonly found in ordinary comets and can be an important driver of activity at larger distances. It may have been lost from read during its long residence in the warmer asteroid belt, or the object may have formed in a region that contained less of it. One clear detection answered the question of whether water was escaping while creating a new question about what was missing. Main belt comets are valuable because their orbits suggest that at least some formed near their present region, rather than arriving recently from the Kuiper belt or Oort Cloud. A typical comet from those distant reservoirs usually follows a more elongated or inclined path and remains strongly influenced by the giant planets. Main belt comets travel among asteroids on comparatively low eccentricity, low inclination orbits that can remain stable for long periods. Computer simulations are needed to test whether a particular object could have migrated into the belt from elsewhere. In many cases, the orbit is dynamically consistent with local formation. Several main belt comets are also associated with asteroid families, groups of fragments created when a larger parent body was broken apart by a collision. Family membership strengthens the possibility that an active object shares the local history of nearby asteroids. This local ice matters for the history of water in the inner solar system. Earth formed in a region where high temperatures made it difficult to retain large amounts of water ice during the earlier stages. Some of its water may have arrived later in impacts involving water-rich asteroids and other small bodies. Main belt comets show that icy material was not restricted to the most distant parts of the solar system, although they do not by themselves settle how much of Earth's water came from any one population. Their chemistry can help test delivery models. Scientists compare ratios of isotopes, which are different forms of the same element, in water from Earth, comets, meteorites, and asteroids. A close match may suggest a shared source or similar formation conditions. A mismatch can show that a population was not the dominant supplier. Direct measurements from main belt comets remain limited, which is one reason each successful gas detection attracts so much attention. Another unusual member is 288P, also known by the asteroid designation 300163. Hubble observations revealed that it is not one body but two similarly sized components orbiting each other. The pair also produces a dust tail, making it the first known binary asteroid classified as a main belt comet. Evidence from the sustained activity supports sublimation of water ice as the main source of the escaping dust. The two components are separated much more widely than many asteroid binaries of comparable size. They may have formed when a rapidly rotating parent body divided. Sublimation can then influence the orbit of the pair by producing small reaction forces, just as cometary jets can alter the spin and motion of an ordinary nucleus. In 288P, activity, rotation, and binary formation may all be connected rather than representing separate events. A small impact could have exposed its buried ice after the split, or newly created surfaces may have revealed volatile material directly. The exact history remains under study. What makes 288P useful is that it demonstrates how several small body processes can operate together. Collision creates fragments, rotation separates them, ice sublimates. Escaping gas moves dust and applies weak forces. The object is an asteroid, a binary, and a comet depending on which part of its behaviour is being described. This overlap is why astronomers introduced the term active asteroid. Earlier language often assumed that anything with a tail must be a comet. As more objects were discovered, it became clear that a comet-like appearance could result from mechanisms with no sublimating ice at all. A tail is evidence of mass loss. Determining the cause requires examining its timing, structure, repetition, gas content, and orbital setting. An impact produces one of the simplest alternatives. The asteroid belt contains many bodies moving on crossing or nearby paths. Collisions are uncommon for an individual asteroid during a human lifetime, but the belt contains enough objects that impacts occur somewhere within it. A small projectile striking a larger body at several kilometers per second can excavate a substantial cloud of dust. Asteroid 596 Sheila provided a clear example in late 2010. Observers saw that the large asteroid had brightened and developed a coma with unusual plumes. Hubble and the Swift Observatory followed the fading dust. No typical comet gases were detected, and the structure was best explained by an oblique impact from a much smaller asteroid. The collision excavated an enormous quantity of material while leaving the main body intact. Sheila's dust cloud faded rather than returning seasonally. This is what an impact model predicts. Material is blasted outward during a brief event, sunlight pushes the smaller particles away, and the surrounding cloud disperses. Unless another impact occurs, there is no continuing energy source to replace it. P/2010. A2 offered another collision case, although its appearance was very different. It displayed a narrow trail and an unusual X-shaped pattern near the source. Hubble observations showed structures unlike the smooth coma of an ordinary comet. Modelling indicated that the dust had been released during a collision months before the object was discovered, probably when a small asteroid struck a body roughly 100 meters across. The delay between impact and discovery shows why the event itself is rarely seen. Telescopes usually find the debris after it has begun spreading. Astronomers reconstruct the collision by measuring particle positions, estimating how sunlight has moved grains of different sizes, and calculating backward to the likely release date. It is a form of orbital forensics conducted after both asteroids have declined to provide statements. Collisions can also create future comet activity. An impact that releases only dry dust produces an active asteroid but not a main belt comet. An impact that exposes buried ice may begin with a sudden ejecta cloud and continue with slower sublimation. The initial and continuing mechanisms can therefore differ. Repeated observations are needed to see whether activity returns or lasts longer than an impact alone would allow. Rotation provides another major route to mass loss. An irregular object absorbs sunlight and later releases that energy as heat. Because the surface is not perfectly symmetrical, the outgoing thermal radiation produces a tiny net torque. Over a long period, this effect, known as YORP, can speed up or slow down an asteroid's rotation. The force is extremely small, but small asteroids also have weak gravity. Many are rubble piles made from fragments held together by gravity, friction, and modest cohesive forces rather than by the strength of one solid rock. If rotation becomes fast enough, loose material near the equator can slide or escape. Further acceleration can divide the entire body. Active asteroid 311P/Pan-STARRS displayed at least 6 distinct dust tails during 2013. The tails appeared at different angles because they were produced during separate episodes and then rearranged by solar radiation pressure. Hubble images changed noticeably over only a few weeks. The leading explanation is that a rapidly rotating asteroid released surface material in a series of small landslides or shedding events. The body did not release all its dust in one explosion. Separate packets left at different times, creating multiple synchrones, which are structures made from particles sharing similar release dates. To an observer, the result resembled several tails radiating from one object. The asteroid was not growing new permanent appendages. It was leaving dated layers of debris for sunlight to sort. A more complete rotational failure was observed in P/2013 R3. Hubble images showed the object separating into as many as 10 significant pieces over several months. The fragments drifted apart slowly, much too slowly for a violent high-speed impact. Each produced its own dust, creating a small moving group of active fragments. The gradual breakup was consistent with a weak rubble pile body that had been spun beyond its ability to remain together. Sunlight may have increased the rotation over a long period, until centrifugal effects overcame the limited strength holding the fragments in place. The separation speed was closer to a walking pace than an explosion, which is a gentle speed for an event that dismantled an asteroid. Rotational shedding and sublimation can influence each other. Gas jets apply torques and may alter a body's spin. Faster rotation can expose fresh surfaces or open fractures. A landslide can uncover ice, leading to new gas release. An active object may therefore begin with one mechanism and continue through another. Classification becomes a description of the dominant evidence rather than a complete biography. Thermal fracture offers another possibility, especially for bodies that pass very close to the sun. Repeated heating and cooling cause minerals to expand and contract. Different materials respond at different rates, producing stress that can crack rocks and release grains. Dehydration of hydrated minerals may also contribute at high temperatures. These processes are considered particularly relevant to active asteroids such as Phaethon, whose orbit takes it much closer to the Sun than ordinary main belt objects. Electrostatic forces have also been proposed for moving very fine dust. Ultraviolet sunlight and the solar wind can charge surface grains. On a small body with weak gravity, electric fields may be able to lift the smallest particles. This mechanism is unlikely to explain every large dust tail, but it may assist other processes or move fine material near the surface. The active asteroid population is small enough that several suggested mechanisms remain difficult to test in detail. The shape of a dust feature provides clues. Continuous sublimation often creates a tail supplied over weeks or months. A short impact can produce a cone, shell, or sharply dated trail. Rotational shedding may create several tails from separate release events. Fragmentation produces multiple nuclei. Particle size also matters because sunlight pushes small grains more strongly than large ones. Gas detection is more decisive, but it remains difficult. Water vapor is faint, and Earth's own atmosphere contains enough water to complicate observations at many wavelengths. Space telescopes avoid much of this interference but have limited observing time. The object must be active, bright enough, and positioned where the instrument can observe it safely. Even a non-detection does not prove that no ice is present. Gas production may fall below the instrument's sensitivity. The active area may be small. Water molecules can be broken apart by sunlight before they are observed. Dust can remain visible after gas emission has declined. Scientists therefore combine direct searches with evidence from repeated activity and detailed tail models. The number of known active asteroids remains small compared with the main belt population. Their activity is often faint and temporary, so surveys can miss it. An object may look active in one image and completely ordinary in the next orbit. The growing volume of survey data has made citizen science searches useful because human volunteers can notice faint tails, asymmetries, and fuzzy appearances that automated classifications may overlook. NASA's Active Asteroids project uses repeated survey images for exactly this purpose. Future observatories will detect smaller bodies and weaker activity. Repeated wide-field surveys are particularly valuable because they can find an object before, during, and after its active period. Archival images may then reveal that the activity began earlier than the discovery date or occurred during a previous orbit. A spacecraft visit would resolve many uncertainties. Close images could identify vents, fresh craters, landslides, exposed ice, and fragmenting regions. A mass spectrometer could identify gas directly. Thermal instruments could map temperatures and locate buried volatile deposits. Measurements of rotation and gravity would show whether the body is a coherent rock or a loosely assembled rubble pile. The challenge is choosing a target. A main belt comet may become inactive before a spacecraft arrives. An impact-driven object may never repeat its display. A mission designed to study one mechanism could find that the surface has become quiet by the time of encounter. This is a familiar difficulty in comet research, although the asteroid belt adds the possibility that the supposed comet was caused by a single collision and has no plans for an encore. These objects have changed the older picture of a dry asteroid belt separated cleanly from an icy comet population. The solar system did not arrange rock in one container and ice in another. Formation temperatures changed gradually with distance. Materials migrated through the young planetary disk, and later collisions mixed and exposed them. Some asteroids contain hydrated minerals, some preserve buried ice. Some comets develop surfaces so dusty and inactive that they resemble asteroids. An active asteroid therefore gives information even when no sublimation is involved. A collision reveals the structure below an old surface. Rotational breakup shows how weakly small bodies may be assembled. Dust tails allow particle sizes and release times to be estimated. Fragmentation demonstrates how asteroid families and meteoroid streams can begin. The temporary activity turns a faint point into a visible experiment. Main belt comets add another layer because their ice has survived in a region much closer to the Sun than the Oort Cloud or Kuiper belt. They preserve evidence about the distribution of water during planet formation. Their small active patches show how a body can hide volatile material for billions of years and reveal it only after a crack, impact, or seasonal change opens the right route. The distinction between comet and asteroid remains useful, but is no longer absolute. An object's orbit describes how it moves, its composition describes what it contains, its activity describes what it is doing now. Those three descriptions do not always point toward the same traditional label. Farther from the Sun, a related uncertainty appears among bodies travelling between the giant planets. Some remain inactive even though they contain abundant ice. Others develop comas at distances where water should stay frozen. Their unstable orbits can carry them inward until they become ordinary short-period comets, or outward until they disappear from planetary view. Those objects are called centaurs, and they occupy one of the least settled parts of the solar system. Most travel between the orbits of Jupiter and Neptune, moving through the same broad region as the giant planets. Unlike the planets, however, centaurs rarely follow calm, nearly circular paths that remain undisturbed for billions of years. Their orbits tend to be elongated, tilted, and vulnerable to repeated gravitational encounters. The name comes from the centaurs of Greek mythology, creatures described as partly human and partly horse. Astronomers chose it because these objects also appear to combine two identities. Their orbits and likely origins connect them with frozen objects beyond Neptune, while their occasional activity makes them resemble comets. They are not quite ordinary Kuiper belt objects and not yet ordinary short-period comets. They occupy a transitional stage between the two populations. Most centaurs are thought to have started as trans-Neptunian objects. Small gravitational changes, particularly encounters involving Neptune, move them away from their original orbits. Once a body begins crossing the region of the giant planets, each close approach creates another opportunity for its path to change. A centaur passing near Neptune may be pushed toward Uranus. Uranus may later redirect it towards Saturn. Saturn can send it closer to Jupiter, and Jupiter may finally place it on an orbit that reaches the inner solar system. The process is not orderly, and it does not always move inward. An encounter can just as easily send the object back toward Neptune, place it on a different centaur orbit, or eject it from the solar system entirely. NASA researchers sometimes compare this movement with a game of gravitational pinball. The comparison works reasonably well, provided the pinball table is billions of kilometers wide, the bumpers are planets, and a single turn can last several million years. Because their paths cross or approach those of the giant planets, most centaur orbits are unstable over very long periods. Unstable does not mean that the body will suddenly vanish next Tuesday. It means the orbit is unlikely to remain approximately the same across the age of the solar system. A centaur may spend thousands or millions of years in its present region before a planetary encounter produces a major change. This makes centaurs temporary residents. They have usually entered the giant planet region relatively recently by astronomical standards, and they will eventually leave it through another orbital transition. Some will become Jupiter family comets, some will be scattered outward, others may collide with a planet, a moon, or the sun. Their current state is one stage in a much longer dynamical history. The first object recognized as belonging to this unusual population was 2060 Chiron. Charles Cowell discovered it in 1977 on photographic plates taken at Palomar Observatory. At first it appeared to be an asteroid travelling on an unusual orbit between Saturn and Uranus. It had no obvious coma, and there was no clear reason to call it a comet. During the late 1980s, Chiron brightened in a way that could not be explained only by changes in distance or viewing angle. Astronomers detected a surrounding coma and concluded that it was releasing dust. It had begun behaving like a comet despite remaining far beyond the region where water ice normally drives strong activity. Chiron now carries both an asteroid number and a comet designation. It is known as 2060 Chiron and 95P/Chiron. The two names do not represent two objects. They record the fact that Chiron was discovered in one category and later displayed the defining behaviour of another. Its nucleus is much larger than that of most familiar comets. Estimates have varied as observations have improved, but it is roughly a couple of 100 kilometres across. A body of that size has enough gravity to hold some slow-moving material nearby, and observations have suggested jets, dust structures, and possibly material surrounding it in more complicated arrangements than a simple temporary coma. Chiron's activity at great solar distances cannot usually be driven by ordinary water ice sublimation. The temperatures are too low. More volatile substances, such as carbon monoxide, can become gas under colder conditions. Changes in the structure of amorphous water ice may also release trapped gases as the material warms. Impacts and seasonal exposure can contribute by opening new areas of the surface. The activity does not remain constant. Chiron can brighten, develop a coma, become quieter, and later show new activity. A centaur may therefore pass through several observational identities without undergoing a major orbital change. It can look asteroid-like during one survey and comet-like during another. That variability explains why the total number of active centaurs is difficult to measure. Many are faint because they remain far from the Sun. Their comas may be weak and temporary. An object can be observed for years without showing activity, only to release material after a small impact, a seasonal change, or an internal event exposes volatile ice. Some centaurs are large enough to possess features not normally associated with comet nuclei. Chariklo, the largest well-measured centaur, is about 300 kilometers across and has a system of narrow rings. The rings were discovered when Chariklo passed in front of a distant star and briefly blocked its light several times. Chariklo is not usually treated as an active comet, but its rings show that the centaur population contains more structural variety than a collection of simple frozen lumps. Another object, 29P/Schwarzmann-Wachmann 1, behaves much more actively. It travels on a nearly circular orbit just beyond Jupiter and completes one circuit in roughly 15 years. Rather than waiting until it approaches the inner solar system, 29P experiences repeated outbursts while remaining in the outer planetary region. Its brightness can increase suddenly when gas and dust production rises. These outbursts occur roughly every 6 to 8 weeks on average, although they are not controlled by a perfectly regular timer. This makes 29P one of the most consistently active objects known in the outer solar system. The James Webb Space Telescope examined gases around 29P and found several distinct jets. Webb detected carbon monoxide and made the first definitive detection of carbon dioxide around this centaur. The jets appeared to emerge from different regions of the unresolved nucleus, suggesting that the surface or interior contains areas with different compositions. No water vapour was detected during those observations, which is consistent with the very low temperature at its distance from the Sun. The outbursts may involve pockets of volatile gas, structural failures, changing exposure to sunlight, or more than one of these processes. A crust could temporarily contain gas below the surface before cracking. A rotating region could enter sunlight and begin releasing material. A small collapse might expose fresh ice. The object is distant enough that even Webb cannot photograph the detailed surface, so the exact mechanism remains uncertain. Centaurs such as 29P provide an opportunity to study comet activity before water becomes the dominant volatile. Near Earth's orbit, water vapour can overwhelm signals from more volatile compounds. Farther out, carbon monoxide and carbon dioxide become easier to study as major sources of activity. Centaurs therefore show how a frozen body begins changing before it reaches the region occupied by familiar bright comets. P/2019 LD2 offers a clearer view of the orbital transition. It was discovered in 2019 and showed a coma, jets, and a broad tail while moving near Jupiter's Trojan population. Detailed calculations indicated that the arrangement was temporary. The object had entered the region from a Centaur-like orbit and was expected to continue evolving toward the inner solar system, where it could eventually behave as a Jupiter family comet. A Centaur does not become a new physical object when astronomers begin calling it a comet. The change is mainly orbital and observational. It already contains volatile material. As its path moves inward, higher temperatures allow stronger sublimation. A faint cloud becomes a visible coma. Dust production increases. Eventually, the object enters the familiar cycle of activity near perihelion and quietness farther away. This route also works in the opposite direction for some bodies. A comet can encounter Jupiter and be thrown outward into a Centaur-like orbit. Classification describes the object's current motion and behavior, not an unchangeable identity established when it formed. The word dormant creates another source of confusion because astronomers use it in two related ways. Any ordinary comet may become temporarily dormant when it moves far from the Sun. At low temperatures, sublimation weakens, the coma disperses, and only the dark nucleus remains. The comet can become active again during its next inward journey. NASA descriptions commonly refer to distant comet nuclei as frozen and dormant as this temporary sense. An evolved dormant comet is different. It follows an orbit that brings it close enough to the Sun for activity, yet it produces little or no visible gas and dust. The nucleus may still contain ice, but an insulating surface layer prevents solar heat from reaching it efficiently. Accessible volatile deposits may also have become limited to small areas that are not currently illuminated. Every close solar passage helps create this condition. Ice sublimates and escapes, carrying small dust grains with it. Heavier particles may not reach escape speed and can fall back. When the gas disappears, the remaining non-volatile material collects on the surface. Over many returns, this process builds a dusty mantle. The layer can be only a modest thickness and still reduce activity greatly, because loose, porous material conducts heat poorly. The ice beneath it remains colder. Gas has difficulty finding a route outward. A comet that once produced a large coma may become almost indistinguishable from a dark asteroid. The condition can reverse. An impact may break through the mantle. Thermal stress may open a fracture. A cliff can collapse. Rapid rotation may cause a landslide. Once fresh ice is exposed, the supposedly dormant body can become active again. Dormancy is therefore not the same as death. The comet is more like an old building whose heating system still works, but is hidden behind several locked doors and a cupboard no one wants to move. A sufficiently energetic event can open a route. An extinct comet is usually defined as a nucleus that has lost nearly all of the accessible volatile material needed to produce activity. It may consist mainly of dust, rock, and chemically altered residues. Even at perihelion, heating does not create a detectable coma because there is too little useful ice left near the surface. The distinction between dormant and extinct is difficult to prove. An inactive object cannot easily be drilled from Earth to check whether ice remains several meters below the surface. A lack of visible activity may mean that the volatiles are gone, or it may mean that they are sealed away. Astronomers often use terms such as inactive, dormant, extinct, or dead with some caution, because the evidence rarely provides a perfect boundary. ESA estimates that a typical comet may remain active for only a few hundred close solar passages before material loss weakens it, causes it to break apart, or allows a residue-rich surface layer to insulate the remaining ice. The exact number varies greatly with nucleus size, orbit, composition, and activity. A small comet passing very close to the Sun can change much faster than a large one, with a more distant perihelion. When a comet becomes inactive, its tail and coma vanish, removing the easiest clues to its origin. Astronomers then examine the orbit. A body following an elongated path strongly influenced by Jupiter may be a former Jupiter family comet. A low Tisserand parameter relative to Jupiter can support that interpretation, although orbital measurements alone do not provide absolute proof. Surface darkness offers another clue. Comet nuclei are often darker than typical asteroids because their surfaces contain carbon-rich compounds and processed dust. Infrared observations can measure how the surface absorbs and emits energy. Radar can estimate shape, rotation, and roughness. Spectroscopy may reveal minerals or compounds consistent with cometary material. One proposed dead comet is the near-Earth object 2015 TB145. Radar observations during its close approach in October 2015 produced images that happened to resemble a human skull, which gave news reports a convenient Halloween theme. Infrared measurements indicated that it was very dark, and scientists concluded that it was probably a comet nucleus that had lost much of its volatile material after repeated passages near the Sun. The skull-like appearance was an accident of radar lighting, viewing angle, and a roughly rounded shape. The object does not contain eye sockets, and there is no evidence that dormant comets organize seasonal publicity. Its scientific interest comes from the possibility that some near-Earth asteroids are former comets, whose visible activity has ended. A more recent example shows how difficult the boundary can be. The near-Earth object, 1998 SH2, was treated as an asteroid for years because earlier images showed no obvious coma or tail. During a close approach in August 2025, researchers found that it was not appearing where purely gravitational calculations predicted. Precise measurements revealed non-gravitational acceleration consistent with weak outgassing. Powerful ground-based telescopes then detected a faint but clear tail. In July 2026, NASA's Jet Propulsion Laboratory reported that the object would receive the additional comet designation P/1998 SH2. It had looked like an asteroid because its activity was too weak for most previous observations to reveal. Its motion provided the first strong clue that gas was escaping. This case also connects dormant comets with the newer category known as dark comets. These bodies show measurable non-gravitational changes in their orbits, but have little or no visible coma or tail. The acceleration suggests that material is escaping from the surface, yet the amount of accompanying dust may be extremely small. A dark comet is not necessarily extinct because an extinct body should no longer produce significant outgassing. It may instead be weakly active, unusually dust-poor, or active in gases that are difficult to detect. The label describes the observational puzzle rather than one confirmed internal structure. Discovering these hidden objects matters for more than classification. Cometary outgassing changes an orbit slightly. For ordinary astronomy, the effect can be an interesting measurement. For planetary defense, it must be included when researchers predict where a near-Earth object will travel years or decades later. An asteroid follows gravity and a few smaller effects such as sunlight pressure. A weak comet also carries a changing set of natural thrusters. Jets can turn on and off. Their direction changes as the nucleus rotates. Activity varies with solar distance and season. Ignoring that force can cause a predicted position to drift away from the real one. The same hidden population helps explain meteor showers that have no obvious active parent. A dormant or extinct nucleus may continue travelling along the orbit where it once released dust. Earth can cross the old debris stream every year, while the parent object itself looks like an asteroid. The meteors preserve evidence of activity that the nucleus no longer displays. Dormant bodies can also become active unexpectedly, which is why repeated observation matters. A survey image may show no tail. Another image during a later return may reveal a weak extension. Archival photographs can then be examined to find earlier signs that were missed. an apparently sudden discovery may be the result of improved instruments rather than a genuinely new behaviour. Centaurs, dormant comets, extinct nuclei, and dark comets are hidden for different reasons. Centaurs are hidden by distance. Dormant comets are hidden by their insulating surfaces. Extinct comets are hidden because their active phase has ended. Dark comets are hidden because their material loss produces motion without an easily visible display. They demonstrate that a comet does not need a bright tail to remain part of the comet population. The visible coma is a temporary condition. The nucleus can spend almost all of its existence looking like an ordinary point of light. At the other extreme are comets whose activity becomes so large that they dominate the night sky, attract observers who have never used a telescope, and receive a title based entirely on how impressive they appear from Earth. Great comets are not separated from other comets by origin, orbital period, or chemical composition. They are ordinary cometary bodies placed in unusually favourable circumstances and producing an exceptional display. The phrase Great Comet is a descriptive and historical label rather than a tightly defined scientific class. It is generally applied to an object that becomes unusually bright and prominent, often visible without optical equipment, and sometimes visible during daylight or bright twilight. The label is normally given after the performance rather than before it. Predicting that a comet will become great is much easier than arranging for the comet to cooperate. Several factors must work together. The nucleus must release enough gas and dust to create a bright coma and tail. A large nucleus helps because it contains more material, but size alone does not guarantee strong activity. The surface must contain accessible volatile ice, and enough of that surface must be warmed. The distance from the Sun is crucial. A close perihelion provides intense heating and increases gas production. Sunlight also illuminates the released dust more strongly. A comet that remains outside Jupiter's orbit may be scientifically important, while staying visually unimpressive to anyone using only their eyes. Distance from Earth matters as well. A moderate comet passing nearby can look brighter than a much more active object on the far side of the Sun. The direction of the tail, the angle of illumination, and the amount of moonlight in Earth's sky all affect the view. Dust can create particularly impressive displays because it reflects sunlight efficiently and may form a broad, curved tail. When the comet lies nearly between Earth and the Sun, forward scattering can make dust appear much brighter. Light passes through the cloud and is redirected toward the observer, rather like the bright glare seen when sunlight shines through dust on a window. The window is optional, but household dust remains remarkably committed to scientific demonstrations. A comet can therefore brighten beyond early forecasts without experiencing an extraordinary increase in gas production. The viewing geometry may simply become more favourable. The opposite can also happen. A large active comet may pass through the wrong part of the sky and remain difficult to see from populated parts of Earth. Historically, great comets appeared without warning. They did not follow the familiar patterns of the Moon and planets, and their tails could change visibly from one night to the next. Many societies interpreted them as warnings associated with wars, rulers, disease, or political change. Those interpretations were not based on evidence that comets affected human events. They reflected the fact that rare and unexpected sky phenomena attracted attention during periods when celestial events were widely believed to carry messages. A comet appearing during a crisis was remembered. A comet appearing during an uneventful harvest season had a more difficult public relations department. The Great Comet of 1577 became scientifically important because Tycho Brahe and other observers measured its position against the stars from different locations. The small observed parallax showed that the comet was far beyond the Moon, contradicting the older idea that comets were disturbances in Earth's atmosphere. ESA describes it as roughly as bright as Venus, with a tail spanning an area of sky about 40 times the apparent diameter of the full Moon. Great comets continued to shape astronomy because their brightness allowed long periods of observation. the Great Comet of 1680 was studied by Isaac Newton and others during the development of gravitational orbital theory. The Great Comet of 1811 remained visible for months. Donati's comet in 1858 became the first comet to be photographed. Modern observers have better instruments, but a great comet is still defined mainly by its appearance from Earth. Comet Hale-Bopp became known as the Great Comet of 1997. Its nucleus is estimated to be about 60 kilometers across, and it was discovered while more than 7 astronomical units from the Sun. It remained visible without a telescope for approximately 18 months. Hale-Bopp's large nucleus supported extensive activity. Hubble images showed rotating jets creating pinwheel-like structures around the nucleus. Astronomers also observed sudden outbursts in which dust production increased rapidly. The different volatile ices appeared to be released from separate regions rather than from one evenly mixed surface. Its distant discovery gave scientists time to organize an observing campaign. The comet could be followed as different ices became active at different solar distances. This was scientifically useful and publicly convenient, a combination not always supplied by newly arriving comets. Comet Hyakutake became the Great Comet of 1996 for different reasons. Its nucleus was much smaller than Hale-Bopp's, but it passed unusually close to Earth. The proximity made its coma and tail appear large across the sky. Hubble observed dust jets and several small fragments that had separated from the nucleus and formed their own faint tails. Comet McNaught, the Great Comet of 2007, gained its reputation through an extremely close solar approach and an enormous structured dust tail. It became bright enough to be seen during daylight and later produced a broad fan containing many distinct bands. NASA reported that the tail extended more than 100 million miles, longer than the average distance between Earth and the Sun. These examples show that there is no single recipe. Hale-Bopp was exceptionally large and active. Hyakutake came close to Earth. McNaught passed close to the Sun and developed a remarkable dust tail. A great comet usually combines several advantages, but different objects can reach the title by different routes. Brightness forecasts remain unreliable, because the nucleus is hidden inside the coma once strong activity begins. Astronomers may estimate its size from infrared observations, but active dust complicates the measurement. They must also guess how much of the surface will become active, and whether the nucleus will remain intact. A comet discovered far from the Sun may initially brighten quickly, because highly volatile substances are escaping. Forecasts that extend the same brightening rate inward can exaggerate the final result. Water activity may not increase in the same way. A dust crust may suppress further gas release. The nucleus may fragment. At other times, a quiet comet develops a new active area and becomes much brighter than expected. No prediction can completely account for cliffs that have not yet collapsed, fractures that have not yet opened, or pockets of gas that have not yet escaped. Fragmentation is one of the most important causes of sudden change. A comet nucleus has low density, weak gravity, and limited material strength. Many nuclei appear to be porous collections of smaller components rather than solid monolithic rocks. They can survive gentle conditions for billions of years and still fail rapidly when heating, rotation, or tidal stress increases. Thermal stress develops because the surface warms and cools unevenly. The sunlit side expands while the dark side remains colder. Rotation repeatedly moves material between those conditions. Different minerals and ices respond at different rates, creating cracks. Gas pressure can build below an insulating crust. Sublimation continues beneath the surface, but the gas cannot escape easily. Once the pressure exceeds the strength of the covering material, part of the surface can rupture. The event may produce an outburst, expose fresh ice, or separate a larger fragment. Jets alter the nucleus's rotation. Gas leaving one region produces a reaction force. Across many days, that force can speed up the spin. If the nucleus rotates too quickly, weakly connected sections can pull apart. A close encounter with a planet creates tidal forces. The near side of the nucleus experiences a stronger gravitational pull than the far side. If the difference exceeds the object's internal strength, the comet can be stretched and divided into many pieces. Fragmentation does not always look like an explosion. Pieces may drift apart at only a few meters per second or less. Because gravity is weak, a very small separation speed is enough to prevent them from returning. Each piece continues on a similar orbit and may develop its own coma. The new fragments expose fresh ice. Their combined surface area is greater than that of the original intact body, so gas and dust production can increase. A disintegrating comet may temporarily become brighter, leading observers to think it is strengthening when the nucleus is actually failing. Comet 73P/Schwarzmann-Wachmann 3 provides one of the clearest examples. Its nucleus split into several main pieces during its 1995 to 1996 return. When it came back in 2001, some fragments remained visible. During the 2006 approach, telescopes found that further breakup had produced dozens of smaller components. Hubble images showed individual fragments surrounded by comas and trailing dust. Smaller pieces continued to divide while observers watched. Some brightened briefly and then faded, suggesting that fresh surfaces had been exposed before the small bodies lost most of their volatile material. The fragments remained on related paths, spread along the original orbit. Over time, the separation between them increased. A person looking through a small telescope might have seen only the brightest components, while larger observatories revealed a much more extensive breakdown. Comet C/1999S 4 Linear experienced an even more complete disintegration during its approach to the Sun in 2000. It initially appeared likely to become visible without a telescope, but its brightness became irregular. The nucleus then broke into a cloud of fragments. Hubble detected at least 16 pieces resembling small comets, each producing its own surrounding material. Much of the original mass appeared to have broken into particles too small for the telescope to resolve individually. The object did not merely split into two convenient halves, it largely dissolved into a moving collection of debris. The cause was probably related to solar heating and the weak structure of the nucleus rather than a close planetary encounter. Linear may have been making one of its first visits from the Oort Cloud, so its surface had little experience with the intense heating of the inner solar system. Shoemaker-Levy 9 followed a different route. Before its discovery in 1993, the comet had been temporarily captured into orbit around Jupiter. During a very close passage in July 1992, Jupiter's tidal forces pulled the nucleus apart. When astronomers found it, more than 20 fragments were already arranged in a line. Calculations showed that the pieces would strike Jupiter in July 1994. The impacts occurred over several days, from July 16th through July 22nd. The fragments entered Jupiter's atmosphere at high speed, producing bright flashes, enormous plumes, and dark scars visible in the planet's cloud layers. This was the first time astronomers could predict and observe a major collision between solar system bodies. The Galileo spacecraft saw the impacts directly from its position, while Hubble and many ground-based observatories followed the atmospheric effects. Shoemaker-Levy 9 shows that fragmentation is not always the final event. The pieces can remain large enough to collide with a planet. Another fragmented comet may spread into a meteor stream. A third may leave a chain of small nuclei that continue returning for centuries. More recently, Hubble recorded the breakup of C/2025 K1, also called Comet K1 Atlas. The comet passed perihelion inside Mercury's orbit and was moving outward when Hubble observed it in November 2025. It had appeared intact only days earlier, but Hubble then watched it divide progressively into at least 4 pieces, each surrounded by a separate coma. The results were released in March 2026. Catching the early stages of a breakup is rare because telescopes must be observing at exactly the right time. Most fragmentations are discovered after the pieces have already separated. The K1 observations allowed researchers to compare images taken on consecutive days and see the disintegration developing. Each event helps scientists test different breakup mechanisms. A comet dividing near a planet points toward tidal forces. A body breaking after perihelion may have been weakened by heating and gas pressure. Gradual separation accompanied by a changing spin can indicate rotational failure. Several mechanisms can act together, and the final fracture may occur after years of smaller internal changes. Not all fragments remain visible. Small pieces lose ice quickly because they have a high surface area compared with their volume. A large nucleus can preserve cold material inside. A fragment only a few meters wide can be heated throughout and exhausted over a short period. Dust spreads even faster. Solar radiation pressure pushes small grains away from the orbit. Planetary gravity changes their paths. Collisions grind them into smaller particles. Some enter the Sun, others become part of the broad interplanetary dust population. Larger grains remain near the parent orbit and may produce meteor showers when Earth passes through them. A fragmentation event can create dense new trails, causing unusually strong meteor activity years or decades later. As the stream spreads, the shower becomes broader and less intense. A few fragments may enter stable enough orbits to receive their own comet designations. Others are lost because they become too faint. Their disappearance does not always mean that they have ceased to exist. They may still be moving through space as inactive bodies below the detection limit. This creates a practical difficulty when astronomers say that a comet has died. A missing comet might have disintegrated. It might have become dormant. Its orbit may have changed enough that searchers are looking in the wrong place. It may be returning much fainter than expected. Comet Biela was observed as a periodic comet during the 18th and 19th centuries and was later seen divided into two components. After the fragments disappeared, strong Andromedan meteor storms were linked with debris along its former orbit. The nucleus was no longer visible, but material from it continued intersecting Earth. Other comets disappear for several returns and are later recovered. Improved calculations, larger telescopes, and wide surveys can find an object that earlier observers considered lost. A comet's final fade may therefore be an observational problem rather than a physical ending. When the ending is real, several outcomes are possible. The comet may lose accessible ice and become extinct. It may preserve buried ice and become dormant. It may split gradually into fragments. It may break apart almost completely during one perihelion. It can collide with a planet or the Sun. A gravitational encounter can eject it into interstellar space. The Sun removes many comets without a direct collision. Repeated sublimation reduces the nucleus one surface layer at a time. A comet can survive hundreds of returns while becoming smaller, darker, and less active. Eventually, the remaining object may produce too little material to be recognized. A great comet is not protected from this process. Its exceptional brightness may indicate that it is losing material exceptionally quickly. A wide tail is evidence of a large amount of dust that no longer belongs to the nucleus. The display admired from Earth is built from the comet's physical erosion. Hale-Bopp will return because its large nucleus survived. Hyakutake also continued on its orbit after releasing smaller fragments. McNaught left the inner solar system after producing its enormous tail. Other promising comets, such as Ison and C/1999's 4 Linear, failed to remain intact. Brightness, survival, and size are connected but not identical. A small comet can appear great if it passes close to Earth. A large comet can remain faint if it stays distant. A fragmenting nucleus can brighten dramatically shortly before disappearing. A quiet object can survive many returns because its insulating layer limits material loss. Every category we have followed describes part of this changing population. Jupiter family comets are frequent visitors because the giant planet has shortened their orbits. Halley-type comets return over decades. Long-period comets arrive from the Oort Cloud. Interstellar comets enter from other planetary systems. Sun grazers are defined by how closely they approach the Sun. Main belt comets are recognized by activity in an unexpected orbit. Centaurs occupy the transition between distant icy reservoirs and the inner solar system. Dormant and extinct comets are later stages rather than completely separate origins. Great comets are members of other groups placed in favourable circumstances. Fragmenting comets may belong to any orbital family because a weak nucleus can fail under several kinds of stress. One object could occupy several of these descriptions during its existence. It might begin beyond Neptune, become a centaur, enter the Jupiter family, produce a great display during a close approach, fragment, and leave behind a dormant remnant. The labels change because the orbit, surface, and activity change. This is why no single tail shape, period, or chemical measurement captures the complete identity of a comet. Astronomers combine orbit calculations, brightness records, spectroscopy, infrared measurements, spacecraft images, and long-term observations. Each method describes a different part of the object's condition and history. The nucleus remains the source behind every visible form. When ice sublimates, it creates a coma. Sunlight and the solar wind produce the tails. When the accessible ice becomes sealed or exhausted, those features disappear. When the nucleus splits, each surviving piece may repeat the same process on a smaller scale. Eventually, every individual comet stops being an active comet. It may end as a dark body, a group of fragments, a stream of meteoroids, or particles dispersed through interplanetary space. The material does not vanish. It moves into other parts of the solar system, becomes incorporated into planets and moons, falls into the sun, or travels outward between the stars. The bright visitor seen from Earth is therefore one temporary stage. Before the display, the nucleus may have spent billions of years in a cold reservoir. Afterward, its dust can continue moving long after the coma has faded. Great comet or hidden wanderer, frequent returner or one-time visitor, each object is observed during only a small portion of a much longer physical history. And that brings our journey through comets to a close. We have followed them from distant reservoirs, through planetary encounters, past the sun, and sometimes out of the solar system forever. Some return often, others appear once in thousands of years. A few break apart before the journey is complete. Wherever you are listening from tonight, I hope this quiet tour gave you something useful to think about. If you enjoyed it, please like the video, subscribe, and share it with someone who enjoys calm science. For now, settle in, let your thoughts slow and sleep well wherever you are.